and also alumni of this department. Dr. Srinivas Katkuri is a computer science and engineering faculty at the University of South Florida, USF, United States of America, USA. His research interests are in the areas of smart IoT, high-level synthesis, FPGA-based synthesis, IC reliability, evolutionary algorithms, hardware security, and emerging technologies. His research has been sponsored by NSF, Honeywell, NASA JPL, Department of Defense, Florida DOT, and Florida High-Tech Corridor funding. Dr. Katkuri serves on technical committees of several VLSA conferences and is a peer reviewer for many VLSA journals. To date, he has published over 100 peer-reviewed journal and conference papers. 3 papers he has co-authored or nominated for Best Paper Award in 2003 ASP DAC, 2014 IFIP IEEE VLSI SOC, 2008. Among notable professional service, Dr. Katkuri served as General Co-Chair for 2nd IFIP International IoT Conference 2019, 5th International Conference on Smart Electronic Systems 2019, ACM SIGTA Board 2010 to 2013, as Treasurer, as an Associate Editor of IEEE Concepts on VLSI from 2006 to 2010. And since 2015, he is serving as the Engineering Educator Award from the IEEE Florida Council Region 3. From 2007 to 2008, USF Undergraduate Teaching Award, and 2013 USF Jerome Hirmanak Distinguished Teacher Award. Dr. Katkuri received his doctoral degree from the University of Cincinnati in 1990.
Good morning, everyone. Is it good? You guys can hear us? Good morning, everyone, and it's really I got my bachelor's here in ECE. Then after that, I did PhD from University of Cincinnati. This was in computer engineering, and then after that, in '97, I've been at USF as a faculty. And I really, at the outset, I would like to thank the department, Professor Chandrasekhar Garu and Professor Nayak Garu, for inviting me to be part of this celebration to honor Professor Ramachandran Garu as the retiring Vice Chancellor. So it's my pleasure. So today what we'll do is we'll look at machine learning algorithms in hardware, and I was planning, definitely we would like to for you to have them, and we may not be able to cover all of it, but you will get an idea of where the research is. And I was requested at the end, perhaps we can have a one-on-one discussion on how to possibly do research, what are the research problems, and how. So if you have any questions, I'll be happy to answer. Okay? So let's look at the outline. So perhaps many of you have taken machine learning course before, but I would like to talk about the first 2 modules is about the basics of machine learning, and then we'll talk about what is the current state of the art. Okay? And then we'll look at what are the algorithms. Module 4 really looks at what are the different algorithms that are in hardware, both academia and industry. By no means will be covering all the current state of the art. It's very hard. Possibly it would take maybe a good one course, one semester course to really cover everything in depth. So the idea is that to give you some kind of a I would say gauging of where the state of the art stands, and then we look at some of the work that is ongoing with my research group and so on. So feel free to stop me in between. We'll try to I'll try to clarify, and if not, we can always have available offline later on to further discuss. So first is so what is machine learning, right? So machine learning is actually part of a bigger area called artificial intelligence. So artificial intelligence really is this grand idea of humans have intelligence, we want machines, to be equally intelligent, if not more, right? So that's a grand idea of like, having like a reasoning, planning, processing, etc. So the subset of that is what is known as machine learning. So the idea here is that, as the name suggests, the machines will learn, from us by themselves, and so how do we do that, right? So there are, different types of machine learning. We'll look at that. And today, as you see that machine learning or AI is everywhere, that's a very hot topic. Really one of the breakthroughs is the deep learning, okay? So what is machine learning? Machine learning is a study of the algorithms, basically to improve the performance and at some tasks. So we have some tasks, and we want to be able to improve the performance and with the experience. So what is important here is that there is this experience part that actually is going to help improve the performance. So like humans, we do that, right? We start with something inefficient, and then over a period of time, we accumulate knowledge, we get experience, and we improve and become better. So same idea here. So classical example is, here are different ways of writing your different letters, and handwriting recognition, like number recognition, for example. This is the task. And what you see here is that, there are like, so these blocks here are actually like all different ways of writing the number 2, right? So, and then what you see is that here, the 3 is also looks like 2. And here also. And then here, like 7, for example, also can be confused with 2. And so on. So here is the complexity of the problem, right? That we have a task, and it's not straightforward. The machine, can get confused. Okay, so it gets confused, and we want to be able to design such that this confusion is resolved, right? So that is where. So this is one example of a task that a machine would like to automate. Okay, so. So ML algorithms have been around for a long time, and be able to like automatically learn, without being explicitly programmed, right? So what is the recent development? So these have been around since at least 70s, 80s. The idea was been there. In fact, if you go back, the father of computing, Alan Turing, talked about learning, and talked about. In fact, his idea was that you start a machine just like a kid, because all of us see that there is a born child, and that child actually learns by themselves on a blank slate, and they gather experience from us, from their like playing in teachers and so on. They interact with the world. Turing actually proposed that we shouldn't only now. I think there is a lot more take their own decisions. That is, can they mimic humans, and can they assist humans in daily life? Can they get feedback? Can they learn from human behavior? And even so, can they actually be experts, right? For example, can they do like surgery? Okay, robots that they can do surgery, because humans have a limitation, but machines can actually be very precise. Okay, so that's where they could be very advantageous. So this is a motivation. So there are ML tasks, as I said, like there could be credit card fraud detection, Google car, as I mentioned, now mimicking the brain. Okay, so this is where, okay, so the scale is very high, but if you look at the basic unit, they are very simple. Okay, and so there was that's where like neural networks has come into picture. There was very groundbreaking work that was done in 80s, where there was a study of this neuron, and then equivalently there was an electronic element that was proposed, and then there was backpropagation algorithms and so on. There were nice machine learning algorithms that were invented. Okay, so yeah, ML tasks, in the field of like shopping and so on and so forth, you can use it. So what is the importance of ML? Okay? Why is it important that we look at ML, right? So here are like some reasons. So computations have become cheaper and faster, and so when along with the data storage capacity. So in other words, machine learning now is much more possible today than compared to like 10 years, 20 years ago. Because now we have miniaturized the electronics, the chips so small. I mean, not to the scale. Still the structure of the neuron, artificial neuron, is still very big compared to the size of a human neuron. But we have shrunk it so much, and that actually opens up doors for possibility of building like ML in hardware. So today's status, you have basic first generation algorithms, neural networks, etc. But in future, this is where it's exciting. So we can have self-driving cars, we can have smart homes, we can have smart hospitals, and so on. So this is possible, and so who is using it? So today, if you look at it, ML is already being used in many different industry segments. So financial services, healthcare, shopping, and so you can look at many of let's see what else. So education and so on and so forth. Okay? So one example I can give you recently that I have seen is that, for example, like at Georgia Tech, what I was told is that they have very big classes, like 300, 400 students in one class. And so obviously the didn't know that it was actually a machine that's replying. Okay, at the end of the semester, they let them know that. So this shows that you can actually mimic when it's assignment due, it will tell you it has database and so on. But many of these are like common questions, but there might be some more complex questions where you have to make sense based on the context and so on, right? So about an input samples that you can use it to test, and there is a learning method, and we'll look at what are. I think I'm blocking that side. All right, so two parts. So first is the training part, where you have to train the machine to for a particular task. Okay, so you have a training data, and what you will do is so the moment you are training a machine, you are going to tell what is correct, what is wrong. Okay, only then the machine can try to learn from them. So here is, for example, a bunch of images, and you actually label them. This is a cat, this is a dog, etc. And then the machine learning model is going to basically look at those, and then it's going to have internally you will have some algorithm that will try to now predict. Okay. So if it predicts wrong, then you are going to have error. You are going to basically update some parameters in the model, and then you do this until it kind of does very well on the training data. So once you have that, you will not give only the data that you have used to train, but rather you will give new data. You give new picture of a cat and say, okay, this is a cat with certain percentage of certain confidence level. Okay. So inference is basically is a process of using the algorithm that we have created in the training phase now to actually make a prediction. Okay. So for example, now we give a picture of a cat that it has never come across before. So training versus inference. So the idea here is that the training is basically it's a one-time thing, and then inference is in the field. Now it is actually getting you to do the task that it's supposed to do. Okay. So there are machine learning. There are a few codes here. This is so the thing is, last 30 years, machine learning was a bad word. It was a lot of training. You have to use a lot of data. You have to train it, and then the training would take a lot of time, and the algorithm was not good. It's not perfect. Breakthrough in machine learning is worth like 10 Microsofts, and you know the impact the company has made in personal computing. a director of DARPA. So the thing is that everybody looks at this as a revolution, okay, and this is going to really change the way we live. So in more detail, what are the different types of learning tasks? Okay. So you can have machine learning. There are different sub disciplines here, like supervised, unsupervised, reinforced. So there are 4 kinds of learning tasks. So there's supervised learning, there's unsupervised learning, semi-supervised, and then reinforcement learning. Okay. So let's look at the supervised learning. So input. Okay. And so who provides the correct answer, right? So the human. So when we say supervised learning, there is a supervisor, and that supervisor is human. A cat and dog. It's a very basic example, but we know how to distinguish between cat and dog from other things, right? So we know. So the training data includes desired outputs. You can do classification or regression, and then you can then predict. So here already we kind of went through a little bit in the beginning. So you have predict. So the classification. So here, so cat and dog is a classification problem. Okay, so if I say or a female person, right? This is classifying. So classification is dividing them into classes, right? And so there are many different ways of use decision trees, naive Bayes method, support vector machines, and neural networks. So classification examples, for example, like you have all diagnostic measurements, some disease, like let's say cancer, right? So does it have like a stomach cancer, for example? So disease presence. You take satellite data and see if there is any classification examples. So random forest algorithms are used both for regression and so the other word that I'm using here is continuous value, right? Whereas classification is discrete. That's the difference. So you can have random forest, you can have multiple decision trees that could be merged, and then it will use these trees and try to predict whatever is the problem at hand, like image classification or recommendation engine and so on. Okay? So what you have is you have different trees that are developed, decision trees that are all used together, and then basically use the majority voting to get your final class, whatever is the class's answer, right? Here, for example, to give you an example, let's say one is trying to detect cat, the other is trying to detect dog, maybe third is trying to detect, like, let's say pigeon, and the fourth is something a lion, let's say. Now I give a picture of like a majority vote on that. Okay. Now decision tree actually is like a simpler way of making a decision, and as the name suggests, there is a decision tree, and you can do both regression and classification problem. So for example, here this is a depending on your weight of the car, and if it is depending on the horsepower of the car, maybe you can predict is it going to be high mileage or low mileage. This is one example. So each node actually we are branching on a particular characteristic. So the Bayes name Bayes is a easy to implement algorithm, and for example, classical use is using it for document classification, whether a given text belongs to one or more categories. So for example, like possibly like you give script of Telugu, right? So it might say, okay, this is Telugu. It might get confused with Kannada, right? For example, right? So so here are some examples. So another example is like whether your email is like a spam or not spam, etc. So this is really based on your Bayes rule, okay? The probability, the conditional probability based on that, given your different classifiers, it's going to be able to classify into three, 2 or 3 different classes, and then be able to, given an input, then it will say, okay, this is, it's going to fall into the second class, etc. Now, the support vector machine is you can talk about this as a data science algorithm where mostly it is used for classification problems. Again, so just always remember classification means discrete, regression means continuous. Okay, so here it can be used for both regression and classification algorithms problems, but mostly used for classification algorithms. Right. So when you have something like this, if I give a data point right here, it might get confused that it is actually this side, but actually it belongs to the squares. Okay? So the credit scoring system, for example, is something that actually uses support vector machines these days. So this is a very practical algorithm. So classification applications, there are like facial recognition, many of these are character recognition and so on. So for example, facial recognition, you have a picture, you want to be able to detect the faces. Okay, so this is one example. Also, it's shown that, for example, if you have an original image and if it's being modified, the problem is that when you give perfect input, the machine will have no problem. But usually the problem is when it is imperfect, okay, under conditions which the machine has not. The machines have to be able to work well under the best condition, but actually under the we have learned, okay, in our high school actually works as a pretty good machine learning algorithm. Okay, so there are many different types of regression that can be used. So the linear regression, for example, is a good machine learning algorithm. It can learn from the data and then it can predict. Okay, so here, for example, like you are given the car attributes, and then you want to be able to predict the price. Other examples, for example, in case of farming, given all these conditions, can I predict the crop yield, right? So linear regression, I will not really, just everybody knows the terminologies. You have the response, and then you have model coefficients. So what is it? What does it mean to say? In this case, all it is I have given some data, I fit, and I get these coefficients. Okay, so that is nothing but training. Of course, like there is a cost function, and I want to be able to give between the predicted value and the actual value, and then the coefficients are what are really this is the learning algorithm. So it doesn't have to be like a simple linear regression, as I said, one independent variable, but you can also have like multiple or 2 or more features. So the dependent variables we term as features. Okay. So in ML world, you have this the word feature. Feature is nothing but your input. So here, if you go back, for example, weather, like rainfall, amount of rainfall is a feature. Right? So now the SVM we already have seen in the slide before. You have all this data, and you want to get your hyperplane that fits very well, right? So that the same SVM can be actually adopted, here for with minor changes. So the main idea is is always the same, to minimize the error, and of course you are given a margin of tolerance, and the output typically is like a real number. That becomes very difficult. The reason is that you might have infinite possibilities, but this is so rainfall, for example, right? The number can be anything. The predicted rainfall can be anything. There is no possible number. So in that case, like what one correct answer. But in that case, what you do is you want to be in the vicinity with some error. So that's fine, right? Decision tree regression, again, same ideas, like you can basically build a tree and you kind of have these, the edges are not shown based on the weight and so on. You're going to go to a particular path and then you say that is my answer. So here, for example, it is trying to predict the outlook and the temperature, like the weather, based on certain features. Okay. So the regression applications, there are many, like you could, for example, financial portfolio prediction, predicting house values, predicting like the angle of the steering wheel when you're navigating a car. These are all examples of regression applications. Any questions so far? I'm just going through the slide. Temperature is going to be tomorrow, for example, right? And or whether it's going to be cold or hot. So here it's regression because you have a number that is on a continuous scale, whereas it's a classification where it's cold or hot. Okay, so these are like two examples. Now, in terms of like if you look at the visualization, classification typically has a very clean separation between the two classes of data. Okay, so that is, whereas in regression really it's going to be through the data, and then this whatever you have fed now is can be used for predicting new values that was never there in your actual data. So that is the supervised learning. So supervised learning is that you give data with answers, correct answers, and it's going to come up with an algorithm that will do very well on the trained data, and then after that you will independently be able to predict, operate, and be able to give you answers on inputs that it has never seen, right? So contrast that with unsupervised learning. Unsupervised learning means that there is no supervisor. Okay, there is no one to tell you that this is a good answer, this is correct, this is wrong. Okay. In fact, this is what is going to be, it's more obviously more challenging, but currently I would say that a lot of research is really in supervised learning. Okay, unsupervised learning, not a whole lot is happening just because it's very difficult. Okay, it's very difficult, and but however, the concept is there. There are some algorithms are there, and they are also being used. Right, but still, just if you look at the cat and dog problem, right? If I don't tell what is cat, what is dog, it may not. It's just a label that I'm giving. But if you look at unsupervised learning, if I give you that data, maybe it will group all cats. It doesn't say it is cat, but it will say class 1, class 2, and so on. Right? It still is useful. And we are just saying that, okay, this is the correct answer, this is the wrong answer. So a lot of research actually is open. Okay, so how does it actually learn? So one of the classic ways is that it forms clusters. Okay, so clustering is what is done. Basically, it creates internal representation, forms clusters, extract features. There is some slight noise because you don't tell what are the outputs, and but how does it actually work? It's going to form clusters, and this can be used actually when the data is very low. Okay, so when data is very low, and it forms so clustering and association. These are the two common tasks, and this is a new frontier. Because most big data sets do not come with labels. Okay? So unsupervised learning, you have a raw data in production. So dividing the population into number of groups is similar. Okay? So it has to, there's a concept of similar two objects being similar, so they belong to the same class, and not similar. So most common method of clustering is a k-means clustering. This is a classical algorithm that is used to cluster. And so if you are given the data, it's going to basically cluster. So here, for example, just the distance, right, between the two. So all these are like one bunch of points that are away from this bunch of points, and this one. These are three different clusters, so three different groups. Okay. So this is a very powerful tool, and the main objective is to minimize the sum of distances between the points and their respective cluster centroids. Okay? So that is the main objective. So how does it actually work? So you choose first a number of clusters, and then select random points as data as a centroid. Okay? So you randomly choose a number of clusters, start with random points as centroids, and now you assign all points to the closest cluster. Okay, and then you recompute the centroid now that you have assigned. So there are now different, the number of points change, so centroid changes. So you adjust the centroid again, and then you repeat this until like there is stability in the centroid. So very simple algorithm. Okay, so here is visually we can see that you start with the original data set. And then you start with like, okay, I'm going to start with the two classes, so the red and purple, right? And then this is the next step. So the points that are closest to the red are colored red, and then this one closest to that are colored. And so now once we do that, we actually move the centroids to different. So the red move here, and then the purple move here, like that. So you see finally that these two are nicely clustered, and so this can be done automatically. Okay, so very simple algorithm. So the association rules basically now establish associations among data objects between large databases, and so discovering these relationships in large data set is what is needed. For example, like people that buy a new home, most likely they'll buy new furniture. Okay, this is really good for somebody who owns furniture shops. Okay, if they know who is going to buy it, then they know their market, right? So this kind of association is going to be very knowledgeable. Of course, there are two aspects of why we do all this ML, right? One is, profit. Companies want to make money. They want to make this efficient. They want to make money, right? The second thing is, of course, we want to improve the human condition, right? We want to be able to solve the problems in terms of your health, better living, better quality of living, safety, etc., etc., right? So there are like two aspects of it. Both are important, and so here is one example where that is useful for somebody who's commercial, right? So here's another example looking at your card. You can kind of try to predict like how you could actually organize your store that you have maximum sales. So I mean, this I think we already gone through, like supervised and unsupervised. So now supervised versus unsupervised, if we compare, right? So we can nicely look at like discrete, continuous, and then supervised, unsupervised. In this, what we have is the supervised learning basically can do classification, right? Yes or no, it can tell. And on continuous variables, it can actually tell you, like it can predict values in between. Whereas if you use unsupervised learning on discrete, it can cluster. Okay, it does clustering. And then probably the most difficult problem where you don't have any supervision and the data is very complex, then you are looking at dimension reduction. Okay, so dimension reduction, briefly what it is we know like if you take a function and if you have like let's say a 1,000 features or 1,000 dependent variables, if I can reduce it to 100, then my problem becomes simpler. Okay, so can we reduce the dimensionality of the problem? Okay, this can be done through unsupervised learning. So then comes semi-supervised. Okay, so there's always in between, and what the goal is that here you can actually do a better prediction rule than based on the labeled data alone. Because what it is that humans are also limited, right? They may not be able to do perfectly. There might be scenarios where they may not be able to perfectly label the data. Okay. So if you give wrong training data, then you're going to get a bad machine. Okay, so what if I don't actually completely rely on the supervisor, but have the training data, but also do unsupervised? Okay, so there is some labeled data, but also some unlabeled. So that is the middle ground. Okay? So for example, here you have some unlabeled data, and then there is also some human expert that's probably labeling some of this data the best they can, and then the rest they are leaving it alone. And then then it is going to, so that labeled data is going to be used to train the machine. So the semi-supervised is that you have labeled and unlabeled data, and then now you have a learning algorithm. So then let's look at the reinforcement. So the reinforcement learning is again is basically you can look at it as like what we do humans, right? So there's a child, and the child is learning, right? And the child is learning, and they make mistakes. When they make mistakes, you are going to say, well, it's a mistake. No, you have to correct, right? I mean, that's how we all learn, right? When you are young, then you make mistakes, and you learn from that, you correct, and you become better and better. So here, the idea is that there's some sort of feedback. And so far, what we have seen in the supervised, for example, you have the data, and then you have your learning algorithm. There is never a kind of a feedback or anything. So the reinforcement learning is like a approach that is how we actually learn as humans. Okay, so reinforcement learning is basically where we make decisions sequentially. Okay? And so the output depends on the current input. And so for example, in the chess game, this is one example where you could do a reinforcement learning. Okay, so here is like one example where, okay, I've given like maybe a picture of an apple, and it says no, it's a mango. And the feedback now is that no, it's not a mango, it's an apple. So then it will say, okay, now I've learned, and then next time, it will say it's an apple. So what's happening inside is that it's algorithmically what it's doing is it's adjusting its weights. Okay, it's adjusting its weights, and it's saying that, okay, there is some error here, let me adjust my algorithm. So this is actually more practical, because what happens is that when you have a task, unless you have expert humans, okay, who can perfectly give you the labeled data, and this is not the case in every domain, right? So what happens is that really this is incremental learning, and incremental learning is actually more practical. I start with somebody, and then you take any discipline, right? Somebody starts as on probation, right, as an intern and probation, and learns, and then over a period of time, they actually are reinforcing, and then they're learning, they're making mistakes more and more. So this is over a period of time. Okay, so this is actually a practical way of learning paradigm. So some examples like gameplay, playing, robo in a maze, multiple agents, and so on and so forth. So in summary, what we have looked at is we looked at like 4 types of learning, right? One is supervised, where you learn to predict the output given an input vector. Okay. Unsupervised, there is no supervisor. You just giving the training data, and you learn. And so primarily here it's learned by clustering. And so there is this notion of similarity and dissimilarity that is crucial. Okay. And so therefore, like here, similarity, dissimilarity depends on the domain, right? So for example, facial, position of eyes and then nose and so on and so forth, right? This is similar to a particular face if you have a similar position of eyes, size, and so on and so forth. So there must be some notion of similarity, dissimilarity. Typically, the experts will define this similarity, dissimilarity. Of course, that's the next level of problem is I just give the data, you figure out similarity, dissimilarity. But usually we know what we want to do. What is the end result? I want to detect a person, face detection, right, for example. Then semi-supervised is in between. Like this is where I don't have similarity. Okay? So it has to, there's a concept of similar, two objects being similar, so they belong to the same class, and not similar. So most common method of clustering is a k-means clustering. This is a classical algorithm that is used to cluster. And so if you are given the data, it's going to basically cluster. So here, for example, just distance, right, between the two. So all these are like one bunch of points that are away from this bunch of points, and this one. These are 3 different clusters, so 3 different groups. Okay. So this is a very powerful tool, and the main objective is to minimize the sum of distances between the points and their respective cluster centroids. Okay? So that is the main objective. So how does it actually work? So you choose first a number of clusters, and then select random points as data as a centroid. Okay? So you randomly choose a number of clusters, start with random points as centroids, and now you assign all points to the closest cluster. Okay, and then you recompute the centroid now that you have assigned. So there are now different, the number of points change, so centroid changes. So you adjust the centroid again, and then you repeat this until like there is stability in the center. So very simple algorithm. Okay, so here is visually we can see that you start with the original data set, and then you start with like, okay, I'm going to start with 2 classes. So the red and purple, right? And then this is the next step. So the points that are closest to the red are colored red, and then this one closest to that are colored. And so now once we do that, we actually move the centroids to different. So the red move here, and then the purple move here, like that. So you see finally that these 2 are nicely clustered. And so this can be done automatically. Okay, so very simple algorithm. So the association is association rules basically now establish associations among data objects between large databases, and so discovering these relationships in large data set is what is needed. For example, like people that buy a new home, most likely they'll buy new furniture. Okay, this is really good for somebody who owns furniture shops. Okay, if they know who is going to buy, then they know their market, right? So this kind of association is going to be very knowledgeable. Of course, there are 2 aspects of why we do all this ML, right? One is profit. Companies want to make money, they want to make this efficient, they want to make money, right? The second thing is, of course, we want to improve the human condition, right? We want to be able to solve the problems in terms of your health, better living, better quality of living, safety, etc., etc., right? So there are like 2 aspects of it, both are important, and So here is one example where that is useful for somebody who's commercial, right? So here's another example looking at your card. You know, you can kind of try to predict like you know how you could actually organize your store that you have maximum sales. So I mean this I think we already gone through like supervised and unsupervised. So now supervised versus unsupervised if we compare, right? So we can nicely look at like discrete, continuous, and then supervised, unsupervised. In this, what we have is supervised learning basically can do classification, right? Yes or no, it can tell. And on continuous variables, it can actually tell you, like it can predict values in between. Whereas if you use unsupervised learning or discrete, it can cluster. Okay, it does clustering. And then probably the most difficult problem where you don't have any supervision and the data is very complex, where you are looking at dimension reduction. Okay, so dimension reduction, briefly what it is we know like if you take a function and if you have like let's say a 1,000 features or 1,000 dependent variables, if I can reduce it to 100, then my problem becomes simpler. Okay, so can we reduce the dimensionality of the problem? Okay, this can be done through unsupervised learning. So then comes semi-supervised. Okay, so there's always in between, and what the goal is that here you can actually do a better prediction rule than based on the labeled data alone. Because what it is that humans are also limited, right? They may not be able to do perfectly. There might be scenarios where they may not be able to perfectly label the data. Okay, so if you give wrong training data, then you are going to get a bad machine. Okay, so what if I don't actually completely rely on supervisor, but have the training data, but also do unsupervised? Okay, so there is some labeled data, but also some unlabeled. So that is the middle ground. Okay? So for example, here you have some unlabeled data, and then there is also some human expert that's probably labeling some of this data the best they can, and then the rest they are leaving it alone. And then then it is going to, so that labeled data is going to be used to train the machine. So the semi-supervised is that you have labeled and unlabeled data, and then now you have a learning algorithm. So then let's look at the reinforcement. So the reinforcement learning is again is basically you can look at it as like what we do with humans, right? So there's a child, and the child is learning, right? And the child is learning, and they make mistakes. When they make mistakes, you are going to say, well, it's a mistake. No, you have to correct, right? I mean, that's how we all learn, right? When you are young, then you make mistakes, and you learn from that, you correct, and you become better and better. So here, the idea is that there's some sort of feedback. And so far, what we have seen in the supervised, for example, you have the data, and then you have your learning algorithm. There is never a kind of a feedback or anything. So the reinforcement learning is like a approach that is how we actually learn as humans. Okay, so reinforcement learning is basically where we make decisions sequentially. Okay? And so the output depends on the current input. And so for example, in the chess game, this is one example where you could do a reinforcement learning. Okay, so here is like one example where, okay, I've given like maybe a picture of an apple, and it says no, it's a mango. And the feedback now is that no, it's not a mango, it's an apple. So then it will say, okay, now I've learned, and then next time, it will say it's an apple. So what's happening inside is that it's algorithmically what it's doing is it's adjusting its weights. Okay, it's adjusting its weights, and it's saying that okay, there is some error here. Let me adjust my algorithm. So this actually is more practical, because what happens is that when you have a task, unless you have expert humans, okay, who can perfectly give you the label data, and this is not the case in every domain, right? So what happens is that really this is incremental learning, and incremental learning is actually more practical. I start with somebody, and then you take any discipline, right? Somebody starts as on probation, right, as an intern and probation, and learns, and then over a period of time, they actually are reinforcing, and then they're learning, they're making mistakes more and more. So this is over a period of time. Okay, so so this is actually a practical way of learning paradigm. So so some examples like gameplay, playing, robo in a maze, multiple agents, and so on and so forth. So, so in summary, what we have looked at is we looked at like 4 types of learning, right? One is supervised, where you learn to predict the output given an input vector. Okay. In unsupervised, there is no supervisor. You just giving the training data, and you learn. And so primarily here it's learned by clustering. And so there is this notion of similarity and dissimilarity that is crucial. Okay. And so therefore, like here, similarity, dissimilarity depends on the domain, right? So for example, facial, position of eyes, and then nose, and so on and so forth, right? This is similar to a particular face if you have a similar position of eyes, size, and so on and so forth. So there must be some notion of similarity, dissimilarity. Typically, the experts will define this similarity, dissimilarity. Of course, that's the next level of problem is I just give the data, you figure out similarity, dissimilarity. But usually we know what we want to do. What is the end result? I want to detect a person, face detection, right, for example. Then semi-supervised is in between. Like this is where I don't have to label the data, I have reasonable ones. And then there is data that actually can't do well even to label. So therefore, how about we do partial labeling and partial not labeling, or unlabeled, and then you learn. Supervised learning. So any questions so far? Anything? So that is a image processing problem, right? So you can use like different, you have your 3 channels. For example, your red, whatever, right, the 3 color channels. So the same image can be looked at 3 different channels, look at the percentage, and then that combined with weighted is this color, for example, right? So shape is typically what you do is you actually do some kind of a edge detection, and once you do the edge detection, you are going to create objects, and then once you have the objects, you have a signature. And critical in this object detection is that you have to normalize the size. Okay, that's very important. Okay, once you have normalized the size, then you are going to do some kind of a distance metric. So. Right. But so what you see here, that's a very good, excellent question, because the thing is there needs to be some expert in the domain. You can't just say here is the data, just learn. You need to have some way of, so that's where a lot of these basic algorithm processing, you have to pre-process to get to some cost function. And so that pre-processing algorithms, that is where, I think that's why this is really a culminating point, because we have a lot of algorithms that have been developed for particular tasks like, shape detection and so on. And then you have the hardware that has come through, then you have machine learning algorithms that have matured. All these put together, now this is the time where you can really truly be smart, more importantly very quick. okay, with maybe resources are high, but cheaper, faster, okay, it's possible. Okay, any other questions? Can you repeat? How do you prepare?
Data for a particular machine learning algorithm.
So how do you prepare data for machine learning? So we look at, there are a lot of actually public data sets. So for example, like images, there are a lot of image data sets, 10,000, 12,000, 60,000 images. Some data sets which are small, they are already labeled, some are not. So you could use that data, so because for us to get the data is very difficult, right? So, and these supervised learning algorithms need a lot of data. How good the data is and how well it is labeled, okay, it's very important. So there are a lot of open source data sets. So if you are looking at those problems, you can use them. Any other questions? That's an excellent question.
It's reinforcement learning.
Right.
Similar to Hebbian learning in biological systems.
Correct. So basically, yeah, so you have, I think later on I'll touch up briefly a little bit on that. Yes, sir. Any other questions? Smart as human brain. Okay, that's the ultimate goal, right? Smarter, as smart as a human brain. The thing is that human brain has gone through, the evolution. It has millions of years of evolution. It didn't happen overnight. So the best thing we can do is mimic it, study it in detail and mimic it in the hardware. So the artificial network consists of that communicate by sending signals to each other over a large number of weighted connections, okay? So you have basically these neurons that are really nothing but, if you look at it, they are weighted sum of inputs and gives you some output, right? So each unit receives an input from its neighbor and external sources, and then it's propagated to other units. So this is a test stage. And then apart from processing, there is the task of this adjustment of weights. Okay. So if you go back here, really you see that here it's a weighted sum of these inputs. So that this W here is a set of weights that this cell, this neuron, this artificial neuron that has. So it has. So those is reduced to the problem of finding the right weights. And the system is inherently parallel because all these neurons can actually work in parallel. It's what even the hardware works in parallel, right? So hardware works in parallel, so our electronic hardware. So the neural network then can be built like using your electronics. So a neural network representation, we can look at it as a bunch of these nodes like forming one layer. Like, so this is the input layer, and then you have a series of hidden layers. These are all actually the same, the functions are same, but the weights are different, okay? So as you go along, you have these hidden layers, and then you get to the output layer. So this input layer, for example, just like our human brains, like it's getting input from our eye, it takes an image, right? And then it's sending that input to the input layer, and then that is being is being processed, and you get some output. It says, well, I'm seeing a cat, or I'm seeing a bunch of humans here. Okay. So there is in the beginning, okay, really in the first saying 20, 30 years, machine learning initially had a lot of traction and excitement, and there the structure was you have only 3 layers: input layer, hidden layer, and output layer. Okay, so it's a 2-layer neural net. And then one of the breakthroughs of deep learning is that you have more number of layers here. Okay, and that's why this deep part is nothing but the number of layers from input output. There are a number of so it's n layers deep. Okay. So I kind of like joke with my colleagues in the department, like, you know, you had one layer, you had 30 years of writing papers, now you have more layers, suddenly you have become very smart. But that actually makes a lot of sense, because the thing is that when you look at an image, right? For example, I mean, image recognition is a very classic problem, right? When I look at an image, actually, okay, so it makes it coarse, it makes it detailed. Okay, when I look at a broad view, you know, I'm only looking at you know, just the outlines of the persons. This is the abstraction, right? And then, so as we go from like input layer to the output layer, what it does is it kind of learns at different abstract levels. Each layer is actually, you can look at it as a abstraction. Okay, that's how it becomes intelligent. So humans actually automatically do this. They actually abstract, you know, at many different levels, and that all together is what is the intelligence. So really here, having only one layer was kind of a shortcoming, right? So that was overcome with this. So another thing is that, so the terminology, you have the input layer, each node is a artificial neuron, and this neuron, for example, is giving input to every neuron in the next layer. Okay, and but it's also possible that only a subset, it feeds only a subset of nodes. So so you could have like a sparsely connected layer, right? So now you could say, like, for example, like, let's say, you know, if I take a image processing algorithm, like how many neurons you will have. So in image processing, typically it is going to be, like, let's say if you take a 64 by 64 pixel image, you are going to have that many in the initial layer. So every pixel you will have a neuron. Okay, so you are going to have input layer that's 64 by times 64, and then as you go, and here, you know, if you are only doing like classification, the number of nodes will be lesser here. Okay, will be lesser. So you have a activation function, and whether a neuron must be activated or not is a very simple representation of this. So you have an input, you have an output. So the activation layer decides whether a neuron should be activated or not by calculating the weighted sum. Okay? So the purpose of the activation function is to introduce nonlinearity. Okay? So nonlinearity is important because if you don't use nonlinearity, it simply becomes linear regression. So what we have done in the supervised learning in the beginning. So this nonlinearity makes it to learn better and maybe perform more complex tasks. So commonly used types, there are different functions. A sigmoid is a very common function, and the tan, you know, trigonometric or hyper trigonometric functions, and so on. So basically what you have is you have input layer, the data flows forward, and then the error signals are propagated backward, and those are used basically to now correct the weight. So this is going to be in a feed-forward feedback manner, to kind of learn. Okay? So a neural network architecture, there are a number of decisions to make, like how many hidden layers need to have, what are the number of units per hidden layer, that is how many number of artificial neurons, what is the type of activation function, what's the form of the objective function. So these decisions have to be made. Okay. Alright, so that's really like, that is, so that's sort of like what are the different types of learning what's a different type of neural networks. The neural networks approach is we are actually mimicking the human brain. That's the crux of it. So now let's look at where we stand. Okay. So any questions so far? Any questions on neural networks?
In input and output, but there are two hidden layers inside. It is specific to have two hidden layers.
But typically you can have 4, 5. There's no limit. You can use. But again, there is a classic problem like how many hidden layers are enough. Okay. Sometimes you overdo it Obviously, you can throw a lot more layers. Not good enough. They are enough to do a good job. All right. So,
Example that any example
of the neural network. So I mean, again, you can go right. So you have, or even that face recognition problem. Right? So you have a neural network. I feed just the image, okay, and it can tell me like where the face is, for example. Okay, like so we looked at this. This one right here, faces. In fact, in your smartphones now, when you take an image, it's actually drawing rectangles. If you see, so that is actually it's
Data, if it increase, will it reduce the speed of the system?
So there are two things, right? Training and inference. So training actually is a one-time thing, whereas inferencing goes on real time, right? So the training actually needs a lot of computation. Okay. So for example, like Google has a cloud where I could train. Okay. I can give the data, and I can. So they actually built a special processor we are going to talk about, the TPU. So tensor processing unit. They actually built that for training purpose, because we'll see shortly the data set, how much data we have, and so on. So definitely, the more the data you have, the more label you have, the machine will be smarter. But the training will be a headache. More power consuming, more time, and more, right. Excellent question. Any other questions?
Yes.
So, yeah, go ahead.
How to select the weights for the layers? You don't go to 5 layers.
Right.
So can I use the same weights for the 5 layers or?
Oh, no. That is the learning part, right? So the weights are determined in the training. Finally, when the data is all used to train, you end up with weight values. That is the learning part. When actually each neuron has a set of weight values, okay, that is the training. So I only give the training data, and I say, so for example, I give a lot. That's all I do. I don't give any weights. I don't know. So the whole neural network is going to basically figure out those weights. And when I end up with a set of weights for all the layers, that's your train model. So that's an equivalent of a kid now who has a brain that actually can recognize these faces.
So weights are different for different objects in it.
Yes, absolutely. So you can also do like multiple objects. I mean, if you look at a kid, they can classify hundreds of thousands of objects. So you can do that, but then if you have to, intuitively as you can understand, if you want to do a lot more, you need to have lot bigger, network, right? So yes.
Sir, do we also need to give the, so if we are training for faces, do we need to train?
Excellent question. So the thing is, if you can also tell that this is not a face, definitely that will help, because then it will reduce the confusion. Okay, because see, the more direction supervision that you have, okay, negative answer is also very good. as well as positive, right? Because and kids actually do, like when you look at something, you'll say, "Oh, is this a dog?" Then you'll say, "No, no, it's a wolf. It looks like a dog. It's a wolf." Right? So this is not a dog. It's also a very good. Yes, yes.
Where are these weights?
Right.
Can we?
So there is a fuzzy learning that can happen because really a lot of things are not clear cut, right? So there are some problems where you can't quite say. I mean, for example, like a classical example is like your washing machine. Is it hot enough? Like, hot enough means what? It could be a range of temperatures. So definitely you can do a set of weights. That's also that comes under fuzzy learning.
But fully connected and squarely connected, what's the basic difference between them?
So yes, it's very simple. What it is that although in this figure, so the thing is that if every neuron feeds every neuron in the other layer, then it's fully connected. I don't think this neuron is feeding, so this is incorrect. I'm sorry for that. But like if say, right, is that happening here? Let's
No,
see.
that is not happening.
It's not happening, right? Every neuron is, okay, so this is the wrong example actually. This is incorrect. So it's simply that only a subset of neurons here contribute to a neuron, then that is sparsely connected. That's why kind of completely, it's not completely solved, and but there are some successful high-level problems like there's machine inspection, the biometrics, surveillance, automotive safety, and security. So we have come along very far, but still that problem is not completely solved. So tasks in computer vision, you have either an image or you have video, and if you're given an image, we want to classify or we want to detect some particular object, or we will be able to segment into different objects. And then in video, really in the video, it's so data sets. So as one of the delegates was asking, what about data? For example, MNIST has a database of handwritten digits with 60,000 examples, 10,000 test set, okay, and they are normalized, ready to be used. There is CFART 10, which has 60,000 32 by 32 color images. There are 10 classes, so this is all classified already with 6,000 images per class. There are 50,000 training images, 10,000 test images. So you have all these. So if you are working in this area, then these are available for you. So like that, there is ImageNet, which is a very large visual data set with 14 million images. Okay? 14 million images, 20,000 categories. So the thing is that you could use this database, and you could actually take a subset of images of interest for you. Don't have to use the entire because normally applications are scope. There is a scope, right? So depending on that scope, you can take the images and train and then do your inference. There is another data set which actually it's about 328,000 images and 2.5 million labeled instances. So this is also available. So this is basically 91 object types, and they're in different, in different, modes. Right? So see the same object in different ways, like same person, for example, look differently in different perspectives. Okay. So if you just if I just give you my frontal image, if I take the actual image from the side, it's very difficult to do that. So this variation is very important. The data set has to have that. Then there are other open. So there are lots.
Is it openware or?
Yeah. All these are open. They're all accessible and are available for research. So here is an example. Like in this, so you have kind of identification of different objects like detected person, and so on. So this can be used for detection and segmentation tasks. Okay. So tasks in the computer vision, as I said, like you're given an image, classify, detect, or segment. So here is some example of where like you have semantic segmentation, and so you can look at like this. So this is the grass, cat. So this is basically based on the contour, and there is a sky and so on, and this is like possibly trees, and so this is basically just based on pixels. So this is semantic segmentation. Here, it's actually detecting a cat as single object, and then several object detections and several instances, So this is so depending on the application, you want to be able to do this classification, right? And so given some kind of input like this, you train it and be able to detect these digits. So detection is within the image. You want to be able to kind of identify by putting contours and so on. So here is a very complex image. There are a lot of persons standing, waiting for a bus and stuff. There are buses. There is also this partial. So this is a realistic scenario, right? Where there is some occlusion, right? This one, this car actually is, this truck is being occluded by this one, and even like here, these persons are being occluded. So these are the real problems. So if you can do well on this, there is this success, because the input is never perfect. Okay, input is never perfect. You have to work on that. And what you see here is that there is certain confidence level that is given. So for example, here it says bus with a 98% confidence. Okay, because it has a lot more information. Whereas here it says truck with 63% confidence. The reason is there is occlusion. It cannot see completely, but it can still find that it's a truck with certain confidence. So this is what the machines can do. Okay, machines can actually give a level of confidence. And say this is an object. This is the level of confidence that I have in this kind of detection or segmentation. Okay? So that's very important. Okay? It's very important. If I cannot do a good job, I should let you know. The machine should let you know, right? So segmentation. So earlier you were asking about the shape and the texture. So what you can do is you can actually apply different masks and try to extract different features, and then based on that you could actually try to predict what it is. So any questions? We have 5 more minutes. Maybe we'll stop at this point. So what I would, let me recap what we have done, right? So a bigger picture, right? What is it that we have done? We motivated the machine learning, right? Why machine learning, and what are the applications? The applications are many. And so why is it that we are at this point where we think that machine learning is hot, right? There are many reasons. One is that computers have matured a lot. They are fast, they are cheap. Then the algorithms have matured, like image processing algorithms, and then the machine learning algorithms themselves have become mature. So bringing this all together is possible today. Okay, if you look at like 30 years ago, none of these were available. Machines were very slow, right? Algorithms were not that smart, and the cost was very high. And if they're not miniaturized, I can't really use it in many places. Okay, so that is what I did. So then we talked about different types of learning. What is the basis, right? What's the theoretical basis, right? So we have 4 types, right? Supervised learning, unsupervised learning, semi, which is in between, and then reinforcement learning. Supervised learning is, as the name suggests, there is a supervisor, a human supervisor, who's actually giving exact training data, saying this is what this is, and now you learn, right? So the learning process is nothing but trying to come up with a machine algorithm that can actually learn from this, and then so this is the training part. And then the inference part is actually usage of that algorithm in realistic scenario where we want to be able to give some input that the machine has never seen and be able to do well. Okay? So that's supervised, needs a lot of training data. But unsupervised is that there might be very less data and there may not be a human expert or supervisor be able to annotate it very well. In that case, the data is unlabeled, and now the machine has to learn from that. So one of the classical ways of doing this is clustering. Okay, cluster and then have them as classes. And so k-means clustering algorithm is one common algorithm. So you form clusters, and those clusters, each cluster is a class, so on and so forth. We talked about actually 2 kinds of problems. One is classification, the other is regression. So classification is yes or no, discrete, right? Is this a cat or is this a dog? Yes or no, right? Whereas regression is that actually, what you want to get the output is not discrete, yes or no, but it is continuous. Like the example that we have seen is predicting tomorrow's temperature. Okay, we give all the conditions, humidity, etc., location, and so on, and it comes up with like what is temperature. The temperature could be a real number, right? And so on. So regression. We take about regression. So it's very simple, right? Regression always we fit the equation. So regression and then classification. So we talked about, so supervised learning can be used in regression, classification, unsupervised can not to be labeled it than misdirect, because machines are really dumb, right? You give wrong input and it will train it, and it becomes a wrong expert, right? It's an incorrect expert. So in that case, use semi-supervised. Then lastly, reinforcement learning is where you are going to, it's more incremental, right? You learn, you make mistakes in the field, and then you learn, and then you improve. Okay. So in all this, we also talked about neural networks, which is actually mimicking the human brain. Human brain consists of like 100 million neurons.
Where we had inauguration of the symposium. This exact location for this lunch is just beside the inauguration venue, just in the quadrangle of the building.
And then what you do is you apply filters on these, and then whatever you get, that is basically the output of the convolutional layer. And then activation layer is introduces the nonlinearity. It's basically whatever features that you have learned from the convolutional layer. The activation layer then introduces nonlinearity. The common activation functions are these, like sigmoid, rectify linear unit. So the ReLU is a convolution layer and a sigmoid. So these are like fully connected layers in these experiments. Then subsampling is basically what it's doing is it's trying to reduce the dimensionality. Okay, so one of the problems is that as you said, the complexity is high. Like if you take, let's say, a high def image, you know, the number of pixels is very high. Okay, so we cannot handle, like, so the learning, the training process becomes very complex. So what we are trying to do is we are trying to like downsample. So when you subsample, what happens is that you are reducing the complexity, and you could do some averaging, like you could do max or you could do mean, so that you're not just dropping the data, but you are trying to kind of smooth, or you're trying to kind of like abstract some neighboring pixels into one pixel, right? Sorry. So the so it's a fully connected layer. So you see, like every neuron is connected to every neuron in the next layer, and so of course there is no connection between the neurons within the layer. So intuitively, as the number of layers increase, the complexity increases. So these are like, so using CNN, so convolutional neural networks have become popular these days, and this is the state of the art using CNNs. Like we have looked at all these databases. So for example, like the digits, I think the digits database, you can get as much as 99.71% using CNNs. Okay. Then the smaller databases, you can get pretty good, 99% and so on. But the larger databases, the problem is that of like training. And if you have 12 million images, this is going to be a very, very complex task, right? So so that's the state of the art in terms of like the image, the classification, detection, and segmentation problems. So here is like one kind of, it will show you the progress. So this was a challenge, like a large scale visual recognition challenge based on ImageNet, and in the first year, like in 2010, like every team got at least 25% wrong. Okay, and as the CNNs have become more complex and so on, 2017, about 29 out of 38 teams got less than 5% wrong. So this shows like the progress that's been made over the years, in this area. So now let's look at like the algorithms and the hardware for training and inference. So what we'll do is we'll look at what are the challenges, what are the different types of hardware, and we'll also look at what are the hardware accelerators for these tasks. So the current scenario is that if you look at this plot, you have various, each one of these is like a different, like a CNN kind of a network, trying to work on those database, the image data sets, and this shows kind of like the prediction accuracy and so on. Okay, so the number of parameters, if you see, like the number of parameters is in the order of like millions. So this shows that the complexity of the problem. Okay? So the module. So one of the things is that the models are getting larger and larger. Okay, they are getting bigger. So like 2012, the AlexNet has 8 layers, and then about 16% error. So 1.4 gigaflops. That's the number of operations. Now in 3 years, the ResNet, like this image recognition problem, 152 layers, okay, and 22.6 gigaflops. But the error is much smaller compared to like 16% error. But the problem is that it's 16x times bigger model. Similarly, like speech recognition, you see that there is about 10x. So this is Microsoft related from Microsoft, from Baidu. There's a Google counterpart in China. So, the thing is that the models are getting bigger, and this is not unexpected. It's not surprising because really to do very well, your models have to be complex, have to be big, and so on. So the first challenge, as I said, like model size. So if you have to run a model on like your smartphone, it's too big. You can't run the model on a smartphone. Even like maybe on a connected car, on a self-driving car, the problem is much more complex. Again, the appropriate model that you have for that is going to be pretty big. So one of the big problems is the model size. One challenge is the model size. Second thing is the energy efficiency. This is also very important because we are really constrained in terms of power, right? So for example, like if you take the AlphaGo, the game, so you have 1920 CPUs, 280 GPUs, so you're looking at about $3,000 electric bill per game. That's a huge cost. And on mobile, of course, we know it's a limited battery, and in data center, that's a different problem. Cooling and all that, that's a big problem as well. So third challenge is the speed. The training time is very slow, right? So if you look at like so here, if you look at like like a 10% error rate, it takes about 2.5 days. For about 7%. So for this, so these are like different models, and as we, so this is this you can look at it as a complexity of the model. As the complexity of the model increases, you do have error rate is going down, but the time is going up, like 2 weeks, 1.5 weeks, and so on. So such a long training time obviously is a big problem. So where really is the energy consumed? So the energy is consumed really in terms of, so a bigger model has more memory references, and that references means like you lead to like more energy. So what it is that we are kind of moving data in and out. We are moving the weights. After all, the training model is nothing but a bunch of weights. So you have to read from the memory, you do computation, you move it back, and so on. And if the model is very big, you cannot afford to, it's impossible to put the entire model in the memory. So you'll have to keep moving back and forth, and that's where there is a lot of energy that is being dissipated. Okay? So now let's look at like what's the types of hardware that we have available, right? So we are already familiar with this. So you have a general purpose and you have specialized hardware. Within general purpose, you can have like your regular CPUs and GPUs, whereas special you can FPGAs or even more specialized like ASICs. So the chips are basically integral parts, so they deal with all of the instructions, and so running the basic mathematical computations like your matrix multiplications, that is what drives the algorithm. So so where can the hardware help, right? So typically, like whenever we design hardware, especially when we want to optimize hardware, we look for where is the time that is being spent, right? So you usually profile it and you see, okay, this much time is spent in these operations, so let's try to, what is the bottleneck? And then we try to speed up that bottleneck, right? So where can hardware help? So hardware can help pretty much everywhere. So you can both adapt existing hardware architectures and you can develop new ones. So what kind of improvements can we get? So we can get low latency inference. So if you recall, like we have the training part and then we have the inference part. Typically the inference, many cases it is going to be real time, okay? You are trying to infer something in real time, okay? So for example, you are looking at a road and you are trying to detect like whether a particular type of vehicle is on the road. You have to infer that quickly. There is no, so there are real-time applications that are actually trying to drive this. So obviously hardware will help that. Then another one is higher throughput training, because training is a very complex task, right? Although it is done once, we are talking about, for example, 12 million images, right? So if you have to train, clearly a faster hardware is needed, so you can have higher throughput training, and of course low power, reduced power cost. So all these improvements you can get. So what are the, so how can hardware help? You can speed up basic blocks of computation. So essentially matrix multiplications are very common. So you can speed up matrix multiplications, you can use speed up convolution operations. You can also add data path based on the workload. Remember that we were moving data from the memory, like the weights and the data back and forth. If you can actually cache in between to reduce, so this is a standard caching can be done. Also you can have specific units, like create application specific units which are domain specific, so hardware can help in these ways. So CPU, you already know, like basically the progress, the Moore's law, right? We have exponential growth in terms of the number of transistors. Every 1.5 years, the number of transistors doubles. So still Moore's law is kind of almost at the end, but still that is still continuing. And one of the big developments is at least last 10-15 years is that multi-core, right? Dual core, right, quad core, and even more cores. So this is something. So fortunately, like algorithms, like the learning algorithms can be parallelized. Okay, they can be parallelized. So core like dual core or multi-core machines are very helpful. Of course, remember that the CPU is general purpose, so it is not optimized for learning. You can use it, you have resources, but the thing is that that's the first step, but that's obviously not the best. Then almost by accident, we started using GPUs, right? Graphical processing units. NVIDIA has used that. GPUs were mainly meant for the image processing, right? So but these are like very small processors, lightweight processors that are used in displays, right? So for to have like a very high resolution display, but then turns out that suddenly we have a cheap poor man's like multi-processor machine. So GPUs suddenly have become very popular because the training can be done on the GPU cards. You don't need to have big servers. So these days, like for probably $100-$200, you can get a 4,000 processor, like a GPU processor, that you can put it in your PC, and you can actually do some reasonable AI, like training kind of stuff. And of course, you can actually build your own GPU cluster that can be used for training and so on. So this is another actually sort of reason why machine learning in hardware is becoming more viable, because you can build like a GPU cluster, a very large GPU cluster, with possibly 100,000 lightweight processors, and you can run that for training purposes. Okay, so this is another hardware platform, especially for training. This is very useful. So what we see is that using GPUs, there is about 50x boost in deep learning in last 3 years. So this is very significant. So compare like CPU and GPUs. As I already said, CPU is general purpose processor and spends more area on the cache, whereas GPU is really a lightweight processor, lots of processors, and so you have large volume, lots of computation at the same time, and because these are like lightweight, you can do intensive computation. Another thing is the GPU architecture itself actually evolved to the point where you have like a memory like interspersed along with the processors. So what happens is the data doesn't have to be moved from the main memory or from the disk. So unlike your CPU, which has a small cache, GPUs have actually embedded like memory. So this is a very big benefit of GPUs, because then the data can reside near, and then they can be moved back and forth. Right, so that is so again, GPU initially started off as a display engine, but then they found that this can be used for AI and machine learning. So now NVIDIA itself is using this as a market segment, right? So they are also coming up with the different because again the original GPU card we tried to use for some, not from machine learning but for some big data processing, and what we found was one big problem was still with GPUs was moving data from the memory into GPU and back. That was the big bottleneck. But so NVIDIA addressed this. So now it's much better. So they have evolved architecture where eventually, like many of these problems, one of the biggest bottlenecks is memory. Okay, no matter what, the biggest, so you can have the fastest processor, you can have the biggest memory that you can have, but the thing is, if you can't move the data back and forth very quickly, then that's where we suffer, and that is what the GPUs are addressing. So there is one emerging technology later I'll talk about briefly. We are talking about memory-based that some of you may have known, is that we are looking into in-memory computing. So in other words, data and computation are like interlinked. So in other words, there's never a movement of data back and forth. So that actually is very promising. And in fact, the traditional von Neumann like bottleneck can be resolved using this in-memory computing or in-place computation. Sorry. So I was saying they utilize parallel architecture, massive improvements over CPUs, typically 10x speed improvement. Let's see, so yeah, they can process more functions in a given period of time, and they're better suited for neural networks because the volume of data they can deal with. So what are the problems? Okay, GPUs are great, but power is a problem, right? Power is a problem, and the intensive CPU operations. Like, so there is, you have to, programming the GPU is not straightforward. So you have to actually know the architecture well. So we have done a couple of projects using GPUs. So it's not like you just write the C code and compiles, and no, you have to actually properly, and this always has been a problem with parallel programming. That's why parallel computers never took off, because humans don't think in parallel. It's very hard to think in parallel. So you have to think in parallel, you have to program, and so that is one challenge that you, and So how to speed up matrix multiplication. So the GPUs are actually are good, but the thing is that lightweight processes, really lightweight, because remember that the pixel processing is like a bitwise. These are like very simple process. So what happens therefore is that you don't have enough horsepower in them. Okay, so it takes longer time. So that's why, that is one of the reasons why, for example, Google has gone for a special processing unit like a tensor, they call it TPU, tensor processing unit, and TPUs are now what are deployed in Google's the training cloud, AI training machine, like training cloud. So, but the thing is, it's still is good for like if you are doing, for example, research in this area, you want to train, you could use GPUs. You could have like a GPU that is reasonably well, and for small problems you can still do it locally. Okay, not everybody have to go to Google Cloud and so on. Okay, this is still a viable thing that you can get a like a NVIDIA card, and the prices are dropping all the time thanks to Moore's law. Okay, now the ASIC. So this is the Google has designed this ASIC, which is basically processor designed specifically for one type of task, and the focus is on machine learning. Okay, so it's on machine learning, and they manufacture specifically for ML, and they are obviously much faster. The architecture are optimized for over CPUs and GPUs, and there were recently like benchmarks that were released that show that it's significantly more efficient than comparable GPUs. So I'm not sure if you can buy this for yourself, but I think that these are really accessible through the Google Cloud. Okay. Especially for academic research, Google is pretty open. They donate time on these servers, so you can use it, and maybe for training, and then for inference you can use it locally on an FPGA board. FPGA boards are accessible. If you were to compare these three, here is, so what you see is that the CPU processor like Haswell, which has 18 core, so the area is roughly like half that of the CPU, and even like less than GPU. The speed is lower, 700 megahertz compared to like 2.3 gigahertz. The big thing, as I said, the power wise, it's less, right? It's about 50% less. Idle watts, like when it's not doing anything, what is the power that's drawn? Data per second transfer, so on. So the peak operations that it can is very high. You see that about almost 40 times. So this is obviously it's a special purpose architecture, and they especially like very complex problems, you have to resort to TPUs. Then is your FPGA, and field programmable rate arrays are suitable. So these are, these have become very popular in last decade or 2 decades, and these are like very accessible, and like your Xilinx has very complex FPGAs available to you, like Vertex processors and so on, that you can like custom compile your algorithm onto this and so on. So again, here though, if you look at it in terms of architecture, is a general, you can say general purpose architecture, the general FPGA, right? But there are actually architectures within these that are specific for like automotive, for healthcare, like so. What Xilinx has done is that depending on profiling of application domain, the architecture has changed. Okay? So this is suitable for latency sensitive real-time applications like unmanned vehicles, speech recognition, etc. Yes, sir.
All the GPU architecture is different from the other. It is not.
Yeah. So the TPU architecture is solely on machine learning related. So the architecture is like you have basically like a weighted function. You have weights that are, so you can imagine like you have a cell that can actually do this in parallel. So the architecture is like very specific to the machine learning, right? So whereas here for FPGAs, for FPGAs I don't have an internal architecture here, but FPGAs it's basically the fundamental one is it's a sea of array of gates. Yeah, so array of gates with no commitment to any specific application. So this has rich embedded components like block RAM, lookup tables, flip-flops, etc. And I'm sure you have worked with one of these FPGA boards, especially Spartan or Altera. These. Now Pink is actually a board that is released by Xilinx, where it is specifically for machine learning. Okay, so this is you can compile machine learning algorithm in Python, and you can run it on the FPGA board. Okay, so later we'll do we have done an analysis of the Pink board in terms of constraint platform, what it can do, and so on. So we'll later look at the architecture a little bit. So FPGA versus GPU, if you compare, efficiency and power, FPGAs are actually lower compared to the GPUs, and flexibility-wise, FPGA is more because these are uncommitted logic that can be used to implement your architecture. Then, in terms of the cost efficient, I mean FPGAs are kind of cheaper compared to GPUs. Although I would not, these numbers we have to take it with a pinch of salt, because a basic FPGA board you can get for $100-$200, right? And then even GPU for $100-$200 you can get 1,000 processor GPU these days. Okay, so again, CPU versus GPU, you can look at in terms of, let's say, performance, you can get about 5 to 6 times. And in terms of energy, there is a 6-time reduction in terms of CPU. Nobody does, very serious machine learning, nobody does on CPUs anymore. Okay, we do it either on GPUs plus FPGAs, so GPUs for learning, training, and then like FPGAs for your inferencing. So this sort of summarizes like what you can do, like CPU, like small models, small data sets, basically used for design space exploration. GPUs like medium to large models, and you have a whole framework, a CUDA framework that's given by NVIDIA. So using that you can program the GPUs. I mean, there are a lot of, this is easy, like everybody has access to GPUs. In fact, these days, like if you get a very good display card, more or less it would have a GPU. Okay, so when you buy a computer with a decent display card, you would end up with like a GPU. So it's almost for free. So for a very small problems, you can use that. TPUs are, as I said, it speeds up the matrix computations, the dense vector processing, and there are no custom TensorFlow operations, but this is really like the training workhorse. Okay, and this is accessible through your Google Cloud. And FPGAs, you can do large data sets, but although I would still take a little bit pinch of salt with the FPGAs, the problem again is data. Moving the data back and forth on FPGAs is not straightforward. Many projects that we have done, that's where you would spend a lot of time trying to move data, having high speed, interface bus, to move data and so on. So this is actually not, it's still a problem. Another direction of research right now is that 3D integration, where you have processing as one plane, and then you have the memory sitting on the top. So therefore, like the data is actually like through your bus between the layers. Okay, so that actually is very promising, and that for machine learning is actually scalable. Especially if you look at your CNN model, there's a lot of interconnectivity, right? So if you can do that like 3D, then that's a possibility. That's a big breakthrough. Okay? So again, if you look at the spectrum, like CPU flexibility is the biggest strength, whereas if you go for A6, it's efficiency. And in between, you have both flexibility and efficiency. So, so one example is like automotive it's driving based on machine learning. What you have is, you have neural networks that are used in data center to train the networks running in the car, and then the car itself is going to run now CPU plus hardware accelerator that's actually running the inference engine. Okay, so this is one example where you can. This is actually being done. Google does this locally on their self-driving cars. So other hardware, so this NVIDIA is your GPU stuff. There is interesting architecture, interesting hardware that is recently being developed. There is a company called Movidius. Movidius actually developed a USB stick-based, like a USB interface-based neural computation. So let's look at that. So neural compute stick, this is available openly, like on Amazon. You can buy it for I think $40–50. This you can, and once you have this, you can connect your computer, and is focused on like so-called visual processing units, which are specifically designed for image and video processing. Okay. So this is possible to run like machine learning models like CNN to do inferencing on the data. Okay. So so if you are actually doing research in this area, this is something you can actually use for your experimentation, especially initially when you want to try your algorithms. This is a good platform that you can use. So why is it unique? Like this is becomes possible to process IoT data where it's generated. So this IoT, Internet of Things, I'm sure you have heard of. IoT, the idea is that you have a lot of edge nodes, and each node is really a sensor collecting data and all the time, and then all this data is sent to the server, right? And then you can have applications on the server and so on. But with IoT, the problem is that you have wherever, like let's take for example like a smart city, right? Smart city, you will have sensors at every cross section. Like you might have a camera every cross section, and you might have a camera or other node sitting in like traffic lights, okay, and so on. So these can collect a lot of data, and then using that data you can make intelligent decisions. The thing is that this data is so much that there is no way you can send it to the server. Okay, the network will collapse. You cannot really do that. So in other words, there is a motivation for machine learning or running AI on the node on the edge. It's called the edge, right? Edge intelligence. So you may have heard of the phrase edge intelligence. So these are so-called the edge nodes, and so Movidius, so this neural compute stick, you can look at it as an edge node. Okay, so if you can actually connect this to, for example, like Arduino. You have Arduino. You have Raspberry Pi. These are like cheap processing platforms. They have actually, you can connect this to that, and then what you can do is through Arduino you can connect your sensors like a camera or any other sensors. You can build an IoT node. So you can actually run your machine learning on this hardware. So they have shown different applications. So it compared to like let's say compared to CPU. Of course, CPU has done benchmark. So frames per second. So basically, this x-axis is number of frames per second. So, like for CPU, CPU has done better, but this is not bad. So if you look at NCS2, like these are like different evolutions, right? That knows NCS2 has happened, or maybe no, it is attached to these laptops. I'm sorry. So different laptops they have attached as external hardware, and it has done very well for the cost that you have and for the size that you have. This is a very good performance. So again, so training can be done on a high performance compute cluster, and then inference can be done on accelerators. So any questions so far?
Sir,
Yes.
suppose if we have designed the deep neural network, which is a smaller one, but it is deeper one, and if we have to go for inference, then is it necessary to use all the hardware resources that are present in the FPGA, or it's enough if we use only some part of the hardware that is present on the FPGA?
Yeah. So there is no correct. There is no reason why you have to. So if it's a small network with a few layers, that's fine. In fact, that is better because it will be faster. Power will be consumption will be less, and so on. Yeah. So it's not required.
And one more thing, sir. Can we
Right.
So can we use our own deep DNNs to place them in ASIC?
Yeah, absolutely. You can. The only problem is that you can do that, but the reason is if you look at it. So what I'm saying is that you can do it, but you need to have a very high-end processing node. The reason is that you see the interconnectivity is very high. Every node is connected. Earlier I was saying, if you have 32 by 32 image, for example, so that's a very small image. So we're talking about 30, so about 900. There are 900 neurons in the first layer. Each one is connecting, assuming you have 900. There are 900 connections. So this is a very big. It's like a n squared, right? So the complexity is quadratic. So all that interconnect has to be optimized and so on, right? So you can do that, but I think it needs to, like, it's not a trivial process. Okay. So you can do that. I mean, so you are thinking of like maybe doing that and simulating it, or is that the intent of the question?
Just to find the speed, power.
Yeah, you can do that. Definitely can do. Actually, if you can do it at the gate level, or even if possible at the RT level. I'll be very fast, And if you are actually have a good timing and power estimator at that level, like Cadence has those, right? You can validate that at that level and still be good. Any other questions? Yes.
Regarding this neural compute sticks,
Right.
please give us an example. I thought it is used for
You can do some small amount of training here, but really it's for mostly like to do inferencing on the data. But you can do training. It will be slow. It will be slow. So what it is that you can train it on like a bigger computer, right? Like either on a GPU card or on the GPU card or on the Google Cloud and so on. And then once you have that, download that on your computer. You can definitely do the training, but it might will take a very long time. You might do a small problems like for example, like if you are looking at like let's say handwriting recognition, that's a much smaller problem. You can definitely do both the training and inferencing on the same thing. You don't need to have a GPU. But if you are doing very complex, like within image, if you are doing and the image is 64 by 64, whatever, that is a big, that's definitely a big problem. So any other questions? And a coprocessor, same idea. It's a coprocessor. That coprocessor, for example, was optimized for floating point operation. So same idea. It's not now. Only thing is application is different. Okay. So hardware accelerators are optimized function blocks, basically to offload specific tasks, and these blocks can perform faster compared to the software, so FPGAs are very suitable to host the hardware accelerators. Okay. So the way it is that you have the CPU that handles the rest, and you can, for example, do your matrix multiplications, right, or convolutions. You can offload it to the FPGA board and then collect the results. In fact, in GPU also that's what typically is done. The CPU offloads it to the FPGAs is that you can really try the granularity at which you can try different architectures. But the freedom is a lot, okay? Because you can try very serial architecture, parallel architecture, mixed architectures, and you don't necessarily have to do by hand. You can actually use synthesis tools that come with Xilinx and so on. But so you write it at a higher level, right, and synthesize it and try to use that in your application. So acceleration, you can run a network faster, more efficiently. You can run the inference. Basically, you can just do the inference part. You can also do the training part. If you can. Another thing is with FPGA cards, what you can do is you can build a parallel cluster. So you could have like 4 FPGA cards or 8 FPGA cards on the same. They can run in parallel. In fact, there are companies that actually sell such platforms that are FPGA based. So you can do that. So once you have such a machine, you can then individually compile it onto the FPGA boards and so on. So in terms of processing, if you compare FPGA, CPU, GPU, and DSP, so FPGA does massive parallel processing. The implementation is completely hardware. Okay, so that is a big advantage, right? And because if you can do parallel and if you can do completely in hardware, that gives like a lot of speed advantage. And others, like there is typically software is what it is. So and these are really more like custom, no, not custom, general purpose, architectures to some extent. So this is highly general purpose. GPU is also general lightweight. DSP is also like more geared to digital, like your Macs and so on, but still it is generalized in terms of a DSP application. Let's see, so what else? So you have fast execution processing that's possible. One problem is FPGA is limited space. That's a problem. The memory is a problem. Okay. So this can be a bottleneck. Whereas on CPU, like you can look at it as unlimited space. You have the entire disk for yourself. So there's a lot of space. And the FPGA is not good at certain operations. So like floating point operation. The reason is that the floating point operation, the architecture, the design is like it's too big, right? So it's still at the gate level, it's configurable. So whereas CPU, for example, if the processor has floating point support, they actually have floating point units on the processor itself. Then FPGAs, takes more expertise to program, because you need to do like VHDL or Verilog or System C kind of thing. Whereas the other ones, because general purpose, like C, C++ is good. To some extent, it's difficult. Because you have to, because FPGA is basically just a complete packaged chip, right? So if you want to kind of debug it, there are tools, but you have to learn them. Like chip scope is one. Like in your design, you can use chip scope monitors just like your logic analyzer, but it's not that straightforward. And also the sampling rate, acquisition of data, and results limited. So there is a need to interface to software if you want a host processor, whereas the others, they don't need any special interface. Okay, so always there is always a zero-sum game. If you really want fast, then you need to expend more effort, and there is more complexity. So this is a typical like FPGA-based hardware acceleration. You have an application, you can profile it, and once you profile it, you know what are the time critical functions, bottleneck, and then you program in HDL, and then you synthesize it, and then now you have a CPU plus your accelerator that works together. So there was one research area that in like 10-15 years ago, there's a hardware software co-design. Okay, so this is nothing but, if you look at it, it's a hardware software co-design. Okay, so in the software, you look at what are the complex, like time-consuming operations, moving them to hardware. So I will skip this because we know the advantage of FPGAs. So some of the challenges is that they require significant amount of storage and memory bandwidth. Computational resources are part of billions of operations per second. So just to give you an example, AlexNet convolutional neural network CNN has over 60 million model parameters, which need about 250 megabytes of memory for storing weights, and on a 32-bit floating point representation. Also requires about 1.5 billion operations for each input image. So just to give an example of the complexity of a problem that if you want to run on FPGA. So current scenario is there are not enough storage. Weights are stored in external memory. In future, the expectation is that they'll get more complex with a large number of layers as amount of the data continues, but still the problem is quite complex. So how to overcome? So we still have 15 minutes, right? So let's see, maybe I can so yeah, I think so this kind of compares like what are the different, so there are several groups who have done who have tested machine learning kind of on on the different platforms like Vertex and Zinc boards, Zinc platform, right? So what you see is that you actually get the power efficiency is pretty good. Problem complexity is also pretty good. So you can see that overall like you can use FPGAs, but there is a lot of programming and programming that needs to be done, the custom programming or the design, the digital design that you have to do. So what I'll do is we have like 10 minutes. I can, so this module actually talks about kind of quantization. So the idea is basically simple. Like what it is that see, you have weights, right? You have weights, and these weights are like a floating point, like 2.09. So what it is that if you have weights like this, if you can quantize them, like round them off, okay, that basically makes this floating point into like a integer or maybe even fixed point, just reduce the complexity of the operation. By doing this, what you can do is you can actually improve the speed. Okay, so that's the fundamental idea. And then there is a lot of like you can do analysis of the weights, and you can actually try to group them. So there is a process. So we did work on this, and the paper that we are going to publish on this idea, but I will skip this. So memristors, I was talking about memristors as one platform. So memristor is the fourth device that actually was found. It was in 1970 itself. Leon Chua at Berkeley, he predicted this element. But only recently, last 10 years ago or 12 years ago, at HP Labs, they have found this, they have fabricated this element. And so there's a memristor. So the thing is that the memristor, actually the idea is that you have this, so one of the structures that you can think of is that you have two electrodes, and then in between you have titanium oxide. There are two types of titanium oxide. One is oxygen deficient and the other one is not. And then just by applying the voltage, what you can do is you can move the barrier. Okay, this barrier, right, can be moved electrically. So right now it's in the middle, it has certain resistance. When I move it, it's going to go here, and this has a different resistance value. If I apply another voltage and so that this can be moved away, then this is another. So it can be in two states. Okay. So now we have like two resistive states which can be mapped to 0 and 1. Okay. So this is a discrete. Okay. So this is so the nice thing about this is that this becomes a non-volatile memory. Okay. And not only that, what it is that these you can actually do computation. So that's the nice thing about this. What you can do is you can, let's see if I have don't have a circuit here, a basic NOR gate. I had a slide. So the idea is that the memristor, the nice thing is, can store the data, and you can also compute. You can perform your NOR operation, for example, on the data. So this is actually a very exciting area where there are these crossbars of these memristive elements that actually can store the data. It's nothing but a memory. We have ones and zeros. But not only that, we can manipulate the data. You can compute, perform operations on that data in place. Okay, so this is what is like an exciting, and this actually is closer to our human brain. That's how the human brain works. The synapses actually behave, or the memory cells behave similar to synapse. Okay? That's why human brain doesn't need much power for processing. Like the entire human brain, I don't know, what do you think is the wattage of the human brain? Like any guesses, like how much wattage? So it's about 30-40 watts. That's all. The human brain, the power consumption is extremely efficient. Only 40 watts. And if you take a bulb which is 40 watts, I mean you touch it, the heat, right? I mean that's all. That's all the power that this human brain needs to do such a complex. So that's why our quest is always to get to that kind of a structure. And a lot of researchers believe that we are hit upon. So this memory cell based circuit, okay, is actually going to be someday we are going to be able to build a human brain using memristors with data and the storage and computation the same place with very small amount of power consumption. Right now the biggest problem is power consumption. Okay, the power consumption is so high that it's infeasible to run very long, like 100 million neurons impossible today's hardware. 100 million neurons is impossible. There is no way we can do it because of power. The power consumption is one of the biggest problems. Okay. So if you are looking at so this is known also as neuromorphic computing. So people are looking at, so there is recent, I just briefly show, there is a chip that is built at Ann Arbor which actually has this memristor array that they have integrated, so they actually have done some basic neural networks on that. Let me see what, as I don't have much time, so I'm gonna. So, for example, like they have done some CNN neural networks, like 5x5 image. So it's small. It's a start, but it's very much possible. Okay? So I will stop at this point, and I'll take any questions. I have more about my research, but I'll kind of stop at this point. So any questions? Yes, ma'am.
What makes memory stick and remember the data even though the voltage is too low?
Oh, so it's very simple. Actually, what it is that, see what happens is that you see this layer, right? This has all these oxygen deficiencies. Deficiencies means that it's missing an oxygen atom. So what we are doing is we are applying a voltage between these two terminals and push this. Okay, spread it in a more like so that barrier is moved. And the barrier is moved, what happens is that you have actually the resistance changes. So I don't need any power to maintain that. Okay. So now what I can do is I can reverse this. When I reverse this, these deficiencies go back. Okay. So now what happens is they are only in this region, so the resistance is less. All I need is two different states. So I don't need to use. I don't need to have power. All right. So any other questions? Now it's model. So you can actually build your own memristor-based crossbar array by hand. You can do it, and then you can use SPICE model to simulate it. So it's possible. You don't necessarily have to fabricate. Map algorithms to memristor crossbars. Like one of them is like machine learning, to crossbar array. That's still ongoing. But we are planning to provide some tools that can be used by other researchers to do their research in this area. So any other, we only two values, but actually you can go multiple values. So the thing is, it can be used for more than two. Okay, so that's what actually these guys have done here. This they actually have used it for weights. Let's see. Just looking at like how many weights they have. But yeah, definitely they actually use that for weights. Yeah, it's not in here, but yeah, you can use it for weights.
Like analog device.
Yeah, you can. So the thing is, memristor is not a discrete element. It's an analog element. We are using it as a discrete element for in-memory processing. But if you use analog, then that's what a lot of researchers who are doing neuromorphic are using it as a. So that can also be simulated the spice level. You can do that.
But the material used is silicon.
No, the material is not silicon. The material is the insulator in between actually is titanium oxide. Titanium oxide, there are two of them, titanium oxide and then titanium oxide, like basically TiO2 minus X. X is the deficiency. So you need to have those two. Right? But actually it's sort of easier to fabricate. So right now we are trying to.
Can we develop a model on a FPGA? Like, as you said, LSNet architecture will have various stages. Can we implement it on a FPGA?
Yes.
As an individual, means as a collaboration, some experts can do, but as a research scholar, is it possible for an individual to do design architecture, total deep learning architecture on FPGA?
Yeah, you can do that. Yes, you can do that. Now another thing So the picture is not that great, but this is what is known as the pink board. This is actually a FPGA, okay? And this, so you can write Python code, and you can design your CNN, and you can program that on this board. And you have a lot of help from Xilinx. So this board is also pretty cheap, $100, okay, $100. So maybe 4,000, 5,000 might be even cheaper here. You can, but you can use this to run your own deep neural network on this. There are also that you can take, you can modify, you can download, and you can experiment on this. So we had run, for example, like so one of the projects that we are doing is that the real time, so we have attached a camera to this, and then real time it should be able to detect objects. Okay, so there is what is known as YOLO and Tiny YOLO. You may have heard, right? Tiny YOLO, Y-O-L-O. If you search on that, there are actually like code that you can download. There is a like SDK, which is a Python based. You can run this. You can choose a number of layers. I believe you can do that. Or if you want, you can take a ready-made one and download. Okay. Any other questions? Stop.
Excuse me, sir.
Oh yes.
Sir, we have a feed-forward neural network. If we have to do benchmarking, these feed-forward neural networks can be benchmarked with CNNs. Is it possible?
I'm not sure actually. Maybe sir has more. Anantara sir has more question.
Hardware part I don't know, but this is. Can you repeat one?
Yeah, can you repeat the question?
Neural network, sir. can we benchmark these feed-forward neural networks with CNNs? We have already data sets for CNNs like MNIST, LXNet, such kind of data sets we have. Can we benchmark with, the designed feed-forward neural networks with those data sets?
Yeah. Architecture is different.
See, the feed-forward network is also...
Yes, that is different and this is
If
different.
you look at the feed-forward network, you don't have a convolutional filtering section. But this you can put it at the outer layer, where just you do classification. So the convolutional network was designed only to extract the features and then close all the layers and finally it does the classification. Yes, feed-forward network you can keep it at the last layer with just a classification. We want only the classification. That's what I think most of the people
Right.
keep it.
Correct.
Actually, in CNN, the last layer that has come from that CNN sir. And the feed-forward neural network which I was talking about is our feed-forward neural network. Can
Yes.
we place it?
Yes, you cannot use it because the feed-forward network that you put is also learned using the filtering section. But how you can, suppose if you have already trained and if you have already having the data, yes, you can use it. That you can use it. The entire net, that is what people say the end-to-end. End-to-end learning. So, but if you are breaking that one, take the results and use the last layer feed-forward network. Basically what you are using in the feed-forward network is just a classification. It need not be a feed-forward only. Any classifier you can put it. And even support vector machines also you can put it where you have a two classes or multi-layer. Only thing is the network should be complete. The purpose of designing a convolutional network is to avoid the extraction of the features. Because otherwise also I can extract the features from the images manually. That's what people used to do it earlier. But now this whole thing is combined. Not time.
Okay, so we'll stop. So if you are working, so security can be done at different levels. So we can look at like layout level. We are looking into research in terms of synthesis. Hardware like a high-level synthesis is one of the areas, right? Where how to automatically insert like security options into hardware. Okay, so this is something like you can look into. So let me ask you, like, how many of you here are like full-time PhD scholars? Okay. So, okay, full-time PhD scholars. So maybe if you can tell me like what areas that you are working on, maybe I can give a little bit more insight. You can look at like different things. So hardware security is very hot. In fact, today I was talking to Sriram sir, NASCOM Cyber Security Center of Excellence. He was saying that things like problems that they are interested in, like how to detect if there are any hardware provisions that are inserted into the design. How do you validate? How do you say that whatever design that you have has nothing malicious incorporated into the design? Okay, so this is a very difficult problem, and there is work done, but it's an open problem. And a lot of it has to do with because these days it's all what do you call, like minus fabrication, and everything else is done, right? So entire design is done, and then fabrication is sent out to a third-party fab, and in the fab they might insert anything, right? So how do you detect, how do you design, how can you design your IP, intellectual property, so that when it is sent to like third party, like offshore, like fabrication plant, what if they are inserting something malicious? So how do you detect that? So this is a big hardware tool. Then there is also IoT, like Internet of Things. Right now is a very big topic area, hot area. And IoT, how many of you know like the IoT, how many of you have the background in IoT, like what IoT is? So not a whole lot. So IoT, like as I was saying earlier, Internet of Things, things can be anything. They can be devices, they can be like if you take a smart home, for example, all the appliances at home can be things. If it's a healthcare, a person can be a thing. So you could, for example, have a device that actually they're wearing that can monitor their vitals, and so they're sending data to the server, so it's continuously monitoring the data and it's sending. So that thing could be a person. Okay. For example, if you go for smart farming, like if you have let's say so you could have sensors like in the farm that are monitoring, like if you say smart agriculture, you could have sensors that can look at like what is the pH level, what's the nitrogen content, and all that. So these could be a lot of sensors that are collecting data, sending the data back, and you do some intelligent analysis, data analytics, to find out like what is the, what kind of decisions you can make. So IoT is very big. Internet of Things is a very big area, and it's still it's still at the start. Okay, so if you are working in VLSI and if you are look at IoT, Internet of Things, IoT sensors like smart sensors is a big research area. And smart sensors, when I say smart sensor, means sensor plus AI together on the same device running in that location, right? So so the smart sensors, this is a big topic. So if you can come up with some smart sensors like in healthcare domain or in transportation, agriculture, farming, smart home, smart office, there are like so many different areas, right? So look at IoT, Internet of Things, and there are also a lot of conferences that are coming up, like IoT conferences that you would want to look at and see, like there are state of the art, there are problems that are being addressed. So actually, like the edge nodes that are going to be sitting at different locations, those may not be ASICs, they can be FPGAs, so small footprint FPGAs with running algorithms that can be remotely monitored, that can be where the data can be stored and exchanged. So one of the things is that this so-called filtering of the data is the edge intelligence. So like, let's say for example, like what you have is, let's say you have a smart camera looking at a road, in a smart transportation. Now what you can do is, the camera can look at the vehicles, right? It doesn't need to send the entire image for processing. That image could be processed locally. Okay, so when you have to process locally, like what happens is that they are constrained in terms of power, in terms of performance, and so on. So how do you do AI or machine learning on constrained platforms? This is a very big topic area. Okay, so then what it means is that you have to minimize your machine learning, like inference engine, so that it can still run, right? We are in electronics, basically you could look at like energy harvesting. This is another topic. Like how do you, for example, work with solar sensors right? Or can you harvest energy from like vibrations? There are many different sources. So you could actually work with researchers, like it could be multidisciplinary, where you are designing a self-sufficient system, right? So even like for smart health, there are people are looking at harvesting energy from the human motion. Okay, so you have sensors in the shoes. They actually are generating energy, but they may not be generating the energy that much. So you have a power constraint. So can you like design your application within what you can generate? So this is like power constraint. So this is coupling like energy harvesting with you know, AI and ML and data processing and so on. Then we can talk about, like I was talking about neuromorphic. Neuromorphic computing is another area where using memristors, you know, researchers are looking at building like, there are two problems, right, broadly. One is in-memory computing. So there are, again, if you search the phrase in-memory computing, you will get you know, papers that you can get from the IEEE Explore, their database. But the key idea is that you want to develop an architecture. Again, in VLSI, this is a very interesting problem. Now the thing is, in-memory computing doesn't have to be memristor based. Could also be CMOS based. Okay, so you can look at like how can you store data and also compute that right there. Okay, so in other words, there's no more like a CPU and a memory separate as two blocks, but they are all interlinked. Okay, so this is the next one. If we can do that, actually that solves a lot of problems, because like as I was talking about in machine learning, especially for inferencing, you have to load weights, you have to you know, move the data back and forth. If you have an architecture where the data resides and then weights are all residing in the locally, then you know, you are just doing the computation right there. Okay. So this is another topic area that has lot of traction. People are looking at. We are also looking at that area. Then another topic is sorry, to going back, in-memory computing is one. There is also neuromorphic computing. Neuromorphic computing is where you are actually using, realizing the CNNs or artificial neurons using memristor kind of element. By the way, memristor is not the only emerging element. There are several other elements. You could look at, like for example, spin torque based RAM, STT RAM. Then there is, spintronics. There is also like resistive RAM. There is also magnetic memory. These are all like different types of elements that can be used for this. These are all emerging technologies that can be used. Main thing is that CMOS is coming to an end, right? We know that you know, right now we are looking at what, 7 nanometer, or people are trying 4 nanometer. So pretty much it is going to come to an end. So the thing is, about 10-15 years ago, there were 20-30 different emerging technologies. Out of the 20-30, probably 5 or 6 are right now still in the run. Okay, other technologies kind of tried, but it's difficult to do that. So difficult to kind of, they found that there are bottlenecks, right? Of these emerging technologies, one possibility is that by the way, CMOS technology is so perfect, it's very hard to replace CMOS. Silicon is such a perfect material that it's very hard to replace. I don't think it can be replaced in next 10-20 years completely. Okay. So what is going to happen is that you have a hybrid. So it will be CMOS plus some technology. So if you can investigate some new technology and see how you can integrate it to CMOS, because CMOS still processing is very good. Because all this investment that has been put, right, with millions of transistors, I mean, we are not going to throw away overnight, because there is no other technology that is going to be, that's efficient, fast, and so on and so forth. So it's going to be there. It's going to be next 10, 20 years for sure. Possibly like maybe by the time you retire, CMOS will still be there, but CMOS plus something. I think that is what is the trend is. So if you can look at like some of these emerging technologies like memristor, or then another technology that is big, I think will make a lot of strides is quantum computing, right? So quantum computing is here actually, in the sense that they have realized quantum computers, like very small, like they talk in terms of nodes. The IBM has 70 node quantum computer available actually. It's available for public. I don't know if it is available for outside the country, but that is. But quantum, what it is that you can simulate. You can simulate. There are simulators, and you don't necessarily have to realize it, but simulation is good enough. A lot of researchers do accept that, because not everything we can realize and fabricate. It's very costly, but still you can do a lot of work in this area. So quantum computing is something that you want to look at, because that is going to be what they see is that next 10-15 years there will be reasonable size quantum computer that will be available. Extremely low power, may not be able to replace the CMOS based computer, but it will be reasonable performance but extremely low power. Okay, so quantum is something actually I would strongly suggest those who are starting their career to look at quantum as a possibility. Okay, because, yes sir.
The quantum computers, they require superconductivity, not superconductivity, supercooling.
Supercooling, correct.
5 degrees Kelvin, 10 degrees
Correct,
Kelvin.
correct.
So, maybe very difficult
Right,
for people like us.
very difficult, but the thing is that I think there is research that they are trying to push the temperature towards the room temperature. It may not happen, but
Maybe another 30 years.
yeah, exactly. But I think the way it will be is that the way I see it is that just like mainframe will have somebody would have a computer at that low temperature, you have access, and so you as a terminal you will be able to access that, and so you still can run your computations and so on, right? So that is a feasibility. Yes.
I have another question.
Yes sir.
You said magnetic memories.
Right.
Is it simply like a good old bubble memory?
I would say yes. But now they are able to, so they call it domain wall memory. So domain wall memory, DWM. And I haven't worked on that area, but one of my colleagues did. And domain wall memory, again there the thing is that you will have a small region, just like your magnetic tape, but this is at an extremely small scale. So this is again another technology that you can look at. So in terms of research, I think what it is that many of these emerging technologies, I mean, we cannot implement them because you need a lot of infrastructure, but there is a set methodology where you can validate it through simulation to some extent or the other, right? And that is perfectly acceptable. So just because you don't have access to fabrication doesn't mean you cannot work on it. Memristors, for example, you see that there is a SPICE model, and if you have the SPICE model, you can do a lot of things. You can do a whole dissertation on that, and still you can publish a lot. Okay, so I would say, like, don't get discouraged. Even within US also, we don't fabricate everything. We don't have access to everything, because the way it is that the device people are only focused just on one device. When we ask them to do like scale it, they are not interested. Okay, so they do small systems. So it's kind of simulation. You do some small systems. Once it gets stabilized, they'll start fabricating like bigger structures and so on. So it goes. It's like the same trajectory as your CMOS. Okay. So any questions here?
Actually, Hyderabad,
Yeah.
Microsoft facilities, software where they can simulate and all.
I see.
And 25th January,
Right.
IEEE computing group, they are going to have a workshop. Probably those who are interested in.
Right. So sir is saying that 25th January there is a workshop.
Likely, date maybe is likely.
Yeah, around 25th there's a IEEE workshop
Workshop conducted by IBM.
conducted by IBM on some of these emerging,
No, only on quantum computing.
only on quantum computing. Yeah. So if you guys are interested, please get in touch with Chandrasekhar sir, and so if you can provide that, I think maybe an email or something. Because quantum is going to be 10 years ago, even National Science Foundation, I know, didn't take it seriously. But now they're taking seriously, they're putting a lot of money. They're actually giving fellowships to researchers in that area. They want to develop the workforce. In US itself, there are not many working in quantum. But so if you are like a researcher, starting or looking for dissertation topic, I think quantum is definitely something you should look at, quantum computing, because that's where, and I think once you get quantum computers, you will be experts.
But they should have some exposure to physics.
Exposure to physics, correct. But most of engineer students have some
Quantum mechanics.
quantum mechanics, correct. But we do some quantum mechanics in the, maybe you have to take some courses. These days you have a lot on YouTube. You can, you can get, you can get started on that, and then, right. But quantum is definitely very promising. So any questions or any, so maybe now we can, so those are the areas that I'm working. Crypto is if you are interested, crypto algorithms in hardware is a big research area. Crypto efficiently do it in hardware, low power for example, but without sacrificing the security. So they are called lightweight crypto. Lightweight crypto means that you have cryptographic algorithm that runs on these edge IoT nodes I was talking about, which are in the field. They have to do the exchange the data encrypted. They cannot. They have to encrypt. So if the traditional, if you take AES algorithm, full AES algorithm is very costly in terms of hardware. So you can look at like, how can I take AES algorithm and kind of simplify. So the work there will be at the algorithmic level and also at the block level as well. So I have seen like work where they have efficient multipliers, for example. Just efficient multipliers for crypto is a problem that people have looked at. So I'm just giving an example. But again, there crypto is, if you are interested, crypto algorithm, VLSI architecture, VLSI or FPGAs, either one is a very good topic area. Okay, so maybe we can now go through some of the topic areas that you are looking at, and maybe, if I am knowledgeable, I can give some, like my perspective, what's going on in that area. So maybe you can start with what is the problem area? Parallel.
Hardware security and so how can we just
The idea is that, like, I just wanted to see what are your areas, And yeah, so that's fine, that's fine. So you are working in hardware security for IoT, or are you looking for a problem in that area? Okay, so one of the things is like, for example, you may have looked at PUFs, physically unclonable functions. So IoT node authentication is a big problem. Like a secure node authentication. Like how do you know that somebody hasn't replaced the hardware? Because IoT edge nodes are all out in open. So physically not everything can be secure. So if somebody replaces the chip, how do you know that? So this node authentication using PUFs, like physically unclonable function, PUFs, this is a hot topic area. Okay, so that's one. Then also like even how do you know that if somebody has attacked? If somebody is attacking your node, can you detect that? Okay, that's a general problem, but can you detect while somebody like is taking it off, somebody is tampering with it and so on, can you immediately detect it? Okay, so this is another topic area. Of course, like hardware security, one of the problems is that security has an overhead. When you incorporate security in hardware, you are going to have overhead, power, power, performance. Area is okay, but mainly power and performance. So when you do security, like how can you do that without much overhead? So for example, there might be existing techniques that people have proposed. So how can you take those techniques, incorporate with low power overhead? That itself is a good problem.
Is there any connection between this power consumption and the protocol that we use?
Oh yeah, absolutely. The so protocols are always going to be power hungry. Okay. Within the protocols, there are many protocols. There are some which are lightweight, some which are like heavy. So the thing is that, in fact, what it is in the IoT space, what it is, the edge nodes never directly talk to the data center. So there is this concept of fog nodes, FOG, fog nodes. So fog nodes are more going to be have more horsepower in terms of power, in terms of performance, processing, and so on. So usually a bunch of edge nodes are going to be connecting to the fog. So the thing is that, so can you design like fog and edge nodes, right? How do you do that so that edge nodes can survive with light, low power, but fog nodes are going to, do filtering and so on and so forth. So, yes.
My work is on deep neural networks, designing deep neural networks in terms of for arithmetic circuits. If suppose there are adversarial attacks
Right.
on the training data set of arithmetic circuits, is it related to hardware security, sir? Can we relate it to hardware security?
So your question is that there is an adversarial attack on the training data, where the data is used to train CNNs running on hardware, and the question is that a problem related to hardware? So let's kind of like go through step by step, right? So what you do is that your training data maliciously has some data that is going to be is not going to be safe. It's marked with wrong labels intentionally, right? So that data is used to build a model, and then when that model is deployed, it's going to give you a problem, right? So to give an example, like let's say I'm going to use this on smart transportation. A stop sign, if it will say like go at 45 miles per hour, a stop sign is labeled as go instead of stop, then that will be a really big problem, right? So I think the problem is more at the training level than at the inference level, because once you train, whatever you have is what you have, right? So I think it's a problem at the data level, at the training data level, because there's nothing you can do in the hardware to fix that, right? Because if it says this is a go sign, and that's it, the weights are derived, there's nothing you can do, right? So it would be at the training data. Yes, yes, ma'am.
Sir, on the topic of system on chip.
SOC, yeah. So system on chip is basically you have a processor, you have these days a FPGA fabric, you have memory, everything is integrated on single chip. You have a lot of all these standard protocols, right? USB, you have the bus protocols and everything like that. So SOC, again, hardware security in SOC is a very big problem. Okay. The reason is that, like when I build an SOC and that SOC is sent for fabrication, somebody can put monitors on the buses, for example. So there could be a malicious monitoring of data that's being sent on the bus, and then that data could be leaked, for example, right? So how do you actually detect, how do you design such that there are no such malicious monitors? Okay, that is one. Second thing is that within the design itself, we have a problem sharing a bus, multiple memory blocks on the bus, and so on and so forth. Like, so how do you ensure that you have data that is being it's following a particular protocol. Making a chip break a particular protocol, you can break the system, right? You can crash the system. See, like an attack doesn't have to be very sophisticated. If an attack is successful, if it is such that it stays such that all I have to do, if I can write, if you have a program counter, all I have to do is if I can reset it intermittently sometime, that's it. The system is gone, right? It's as simple as that. Okay. So, but these are like naive attacks. There could be more sophisticated attacks. Okay. So when you are doing the SOC design, how can you actually build in security in SOC? The thing is that SOC, the paradigm is very, the ecosystem is such that you are bringing lot of IPs, right? IP blocks, like processor blocks, memory blocks, all these peripheral blocks, everything they are bringing, and then they are putting it together. It's not like it's not that I have designed those IPs. Because no one can build a SOC from scratch. They have to get third-party IP blocks, put them together, and make them work, right? So one of the ideas on SOC is that can you put like a machine learning block, okay, on the bus, which is actually looking at the traffic, and then it is making sense of it. It's learning what is normal and what is not. Okay, so can you do that? This is an open problem. I mean, people haven't done that. They're looking at it, but still it's a big problem. The nice thing about that is that in SOC, they actually have resources to run complex CNNs or so on, because you have processors, you have FPGA, fabric, and so on and so forth. So you have the possibility of running this in software, running it in FPGA, running even like multiple copies of that. Because what if they compromise one, you have a couple of others running. So all this is also very, so SOC is a very complex ecosystem. The problems are many, and anything you can do to increase the security, that's always the whole dissertation can be done. Multiple dissertations. Yes, sir. Okay.
So is the low power exploration, is it come to a saturation?
That's a good question. My dissertation itself was in low power long time ago. But I wouldn't say it's saturated, but it's not solved yet. The problem is still there. But what you should look, so what abstraction level are you working at? Are you working at like a transistor level, gate level, RT level, transistor level? Okay. So I mean, always circuit structures is always open, okay, in terms of so I'm just thinking in terms of like what could be some good problems, because so like you are correct in the sense that just pure low power is already saturated. There's so many techniques out there that are already implemented in process and so on. So what you have to do is you have to tie that low power to a particular application domain. You cannot have generic circuit. So we were talking about machine learning in hardware. If you look at like circuit structures, building blocks for machine learning, low power. Okay, if you relate to that, then that will be highly publishable. Because then you have some domain knowledge, you exploit that and you design low power. Okay, so that I think is good. Yeah. So I would say generic low power is very difficult because a lot of work has been done. I mean, thousands of dissertations have been done. So I would say tie it to machine learning or tie it to hardware security, right? So so one topic in hardware security that is related to power is, you may have heard of side channel power analysis, right? Side channel power analysis, where you are going to monitor the current that's being drawn, and then using that you are going to try to break the crypto block, trying to break the key that is stored in the crypto block. Okay, so how do you actually mask the power? Okay, if you look at side channel, so there is a differential power analysis, simple power analysis. So these are simple power analysis, nobody does that, but differential power analysis. So how do you do that? So tie it to a certain like crypto low power, highly publishable. Crypto machine learning, highly publishable.
Is there any theoretical limit, like our Shannon limit for communication for this low power?
Yeah. There is definitely a theoretical limit, and I think somewhere in quantum we hit that. Yeah, somewhere in the quantum. But if you are looking at the regular CMOS, we are still way. There's also in low power, I can tell you. Have you looked at like adiabatic computing? So basically, what you do is that usually what you do is when you run the circuit, you dissipate the energy, right? So instead of you consume the energy, instead of like dissipating it as heat, you are going to recycle back to the power source. So what happens is this is a viable thing. So if you look at adiabatic computing, that's a very good. People haven't done that much. So look into that. Even at the circuit level, there is work to be done, because you need to design like a resonating clock circuits that recycle the energy. You can simulate this. You don't even need to build it. You can build it, but simulation in SPICE is possible. Adiabatic computing is one thing. Again, like if you want to look at, there is asynchronous circuits, but asynchronous circuits are extremely low power. Actually, the ideal circuits, if you look at it, because they do work only, they expend own energy only for work that is needed. Because the normal synchronous circuits, the clock is free running, so therefore you waste a lot of energy. Asynchronous has a promise, but it's complex. Okay, work is done, but it's very complex. There is an asynchronous processor that was built in 90s, mid 90s at Manchester, they built a synchronous processor. But still, like in the research in the commercial world, there is no asynchronous. So for example, like if you say, can I do adiabatic with machine learning? So which means that low power machine learning, or asynchronous machine learning, that is low power. The people haven't explored any of this kind of version. Yes, sir.
Sir, in a patient monitoring system, is it possible to design a new type of sensor to extract EEG signal?
EEG signal. Like last week I was at the Smart Embedded Systems IEEE conference. I was the general chair there, and so there were some works they have presented where they collected EEG signal, and they have analyzed, done machine learning and try to detect if there are any like conditions like arrhythmia and other things like that. So in fact, one team, they were really, it was very interesting. They actually built a EEG like leads, everything they have built from scratch, and they were able to collect the signals and so on, and then be able to. It seems like for each one of these signals, you get 6 different waves in 0 to 60 hertz. There are six different, like I think delta, theta, alpha, gamma, beta, 6 of them. So they were analyzing those. So you can look at that, definitely.
Sensor based.
Sensor.
In VLSI design.
From VLSI design perspective, like you can, for example, like look at like let's say you have a sensor that. The thing is that good body contact is needed, right? So if, let's say if there is a patient and they're willing to wear, wear the right, so they can, you can actually, from VLSI perspective, you can actually build a node, right, which actually analyzes the data right there. Okay, so you can do that. Okay, so that's one way. Another way I've seen is that I don't know if they have done EEG, but they have the sensor nodes, but they have either Bluetooth, or they even actually use the body itself to transmit that signal to a variable. So the variable, so you can imagine this is a edge node, and the variable is a fog node, like that. So yeah, there is a possibility of doing that, and EEG. So especially if you say patient context, somebody is at a hospital, that is very much possible. There is also another interesting work from University of Rochester that was presented at this symposium, where they actually built like a variable patch. That variable patch actually was collecting not EEG, but it was collecting things like, so they wanted to find out, like the tremor, like if somebody has Parkinson's disease, like what is the severity, right? And collect a lot of data, and then see like, the pattern and so on and so forth, right? So they actually developed patches, like 6 patches. They collected a lot of data, and that using that data, they were actually able to analyze it. So right now there is this, because of the miniaturized electronics, there is this new discipline called evidence-based medicine. So evidence-based medicine means that you collect lots of data. Right now, the medical health, like healthcare, the thing is that there is a point based. It's a very, like in the entire time span, the doctor, when you look at it, it's only one point, the entire time scale, right? So the thing is that the data is not sufficient. So what it's moving to is evidence based. So collect lot of evidence, and collect lot of evidence and do data analytics, and then be able to give better health care. And that actually leads to another area called personalized medicine. So personalized medicine is that, see, your heart rate may not be same as my heart rate. For my constitution, my genetic profile, demographics and all that, maybe heart rate, blood pressure, all these, there are certain baseline that is perfectly fine, right? Whereas yours might be different. Might be different for some. It all so the thing is, right now, it's medicine is right now one hat fits all solution, right? Everybody takes the same medicine, but in US now they are moving towards evidence based. So for evidence based, they need a lot of data collection. So which means that you need to have VLSI sensors that can collect lots of data on the body and be able to store it and so on. So we are moving to, so if you can build like for healthcare, if you can build a miniaturized system, right, that can collect lots of data, like even like, so this particular, this is Professor Gaurav Sharma, he was the one who gave a keynote at ISRCE. So they built this and they collected data for 2 days at a time from the patient. That's a lot of data. Okay. And so if you can build a miniaturized system that can do some energy harvesting, can collect the data, can store the data locally, and communication is very costly. Communication is very costly. Actually, that's where most of the power, lot of power, because the chips, the processing has come down very much. It's the communication that is actually is a lot power hungry. Okay, so I mean, like wireless, for example, it's like wide open in terms of. So, like in IoT domain right now, we talk about LoRaWAN. LoRaWAN, you may have heard, low power, long range, wide area network. Okay, since LoRaWAN, if you look at it, the technology is being built so that IoT nodes do not have to spend too much energy to share the data, to transmit the data. So healthcare is wide open. It's VLSI, there are a lot of applications, as I said. Any other areas that I can give, I mean, whatever I know. So we'll stop at this point. Is there anything else you want me to do, sir? Yes. Is that good? All right. So in the notes, actually, in the first slide, I have my email address. So feel free to email me, and you can just refer to this workshop, to the seminar. I'll be happy to give, or if I don't know something, I can try to point to the right person who can help. Okay. So thanks a lot for attending the seminar. I hope you learned something, and I really enjoyed giving the seminar. And I thank the department and the college and the university for giving me this opportunity to give this seminar. Thank you, and have a nice day.
A long day. First of all, I'm very thankful to you, sir. So much patience you need to cover the whole glimpses of total machine learning, artificial intelligence. The sir suggested to moderate. It was not in the part. Anyway, it's better. This is actually, typical tradition of the department. Whenever, even when we conduct student test also, Professor D.V.R. Vittal, who is our Pitamaha, so he used to tell us. So someone has to briefly report it, what happened, documentation. So he helped us, because this is going to be a report, and merits and demerits of each technique also he highlighted. Actually, as I mentioned, it is a band. So he started with machine learning, and then he touched upon neural networks, artificial neural networks, and then convolution techniques also he touched upon, and then actually his area of working, that is hardware, where VLSI will come into picture. So when we started our journey, actually he was totally in VLSI, and then he moved to HLS, and then memories. So last time he gave a presentation on memories in the department. Now totally different field is working. So we'll learn from you, sir.
Thank you.
And the different hardwares what are available in the architectures in the technology, right from CPU, what we know very widely, and then GPU. One dimension of GPU we know, we came to know the other dimension of the GPU, and the TPU, and then finally FPGA, where most of our academia is using. And then he highlighted the comparison between each one. Instead of doing only one of them, something like a heterogeneous, like something like a smart hardware model, where some technique will be there in GPU, some technique will be there in hardware or FPGA, so that it made optimization. So that's what he highlighted. And then accelerators also he touched upon. So finally, he briefed about his works in his laboratory. We could not complete everything because of the time management. Because what we requested is, instead of telling only his experience, and we wanted to know from an expert what is VLSA and what are the future trends in VLSA, so that which are useful to our PhD scholars. Mainly, it has to be useful to the PhD scholars finally. And this is what actually happened. And then finally, we are very happy to see the challenges in VLSA domain. What I understood is purely one research is not one problem is not sufficient. Something like an interdisciplinary application-oriented research we have to do it. Even Vishwashraya scheme also is meant for that. So hope we will continue, sir. So sir would like to come in June. We are planning one GAN program. If it is clicked, okay. Otherwise, also department has come forward, and we are going to plan one workshop on total exclusively on machine learning, where we would like to have one day to only exclusively to our research scholars. So especially how to do research and all, full-fledged planning he wanted, he promised is in June. So let us plan for that.
Sure. Yeah, we'll also plan to do hardware, labs.
Yeah.
So we'll actually hands-on. So right now, I mean, we can talk a lot, but once only when you sit down and actually do something, you can feel,
One day may not be sufficient.
No, sir, 5 days.
So it will be 5 days, but one day will be
One day
for the
for
research.
research scholars, PhD scholars. Some cutting edge technologies also he touched upon. This is all about the today's talk. We are very grateful to you, sir. As an alumni of our department, I always tell, I think many of students, there are the students, okay, one is there. Many times I tell to my students, PE students, that one day you have to come like this. And we never forget the department. Finally, no one should forget the department. The department has given everything for us. So we should never forget the department. So any day, anyone comes to you, here from the department of PC, you should be able to help them. So that's what actually I tell to my students. So he is a role model, right? So he has come all the way and he spent his time. Tomorrow also he will be there with us, but in another forum. There is a panel discussion on applications of artificial intelligence in engineering. It is there at 10 o'clock tomorrow at the same place where we have started today inauguration. So all the participants are invited for that, and then followed by there is a networking. Actually, it is under Global Alumni Meet. Actually, we are conducting under Alumni Association. So we have a networking followed by felicitation to our former Vice Chancellor Professor S. Ramchandran, and then we have a lunch. So till lunch, we request you all to be with us tomorrow. So this is all from my side. Now I request our head of the department to give a small memento to our speaker.
Sir.
So thanks a lot. We'll meet tomorrow at 10 o'clock.
No answer.
problem, sir.
Wait. Milk is